Hilbert's Hotel. Imagine a hotel with infinitely many rooms. Not a very large number of rooms, not more rooms than you could count in a lifetime. Infinitely many. Every room is numbered, starting from 1 and going on forever without stopping. And every single room is occupied. A guest in room 1, a guest in room 2, a guest in room 3, all the way out to rooms you could never reach by walking down the corridor. A new guest arrives at the front desk. They need a room. The manager looks at the situation and says, "No problem." He picks up the phone and calls every guest simultaneously. He asks each guest to move to the room with a number 1 higher than their current room. The guest in room 1 moves to room 2. The guest in room 2 moves to room 3. Everyone moves. Everyone still has a room, and room 1 is now empty. The new guest checks in. The hotel was full. A new guest arrived. Nobody was displaced, and the hotel is still full. David Hilbert, the German mathematician who imagined this hotel in the 1920s, was not trying to describe a real building. He was trying to make infinity feel strange in a way that abstract mathematics rarely achieves, and he succeeded. Because most people, when they hear the hotel is full, assume that means no more guests can be accommodated. That is what full means for any finite hotel. But Hilbert's hotel is not a finite hotel, and full, applied to infinity, does not mean what you think it means. Go further. Suppose not one new guest arrives, but infinitely many new guests arrive. An entire infinite busload of people, all needing rooms. The manager is untroubled. He calls every current guest and asks them to move to the room with a number double their current one. The guest in room 1 moves to room 2. The guest in room 2 moves to room 4. The guest in room 3 moves to room 6. Every current guest now occupies an even-numbered room. All the odd-numbered rooms, infinitely many of them, are now empty. The infinite busload of new guests moves into the odd-numbered rooms. A hotel that was full has now accommodated an infinite number of additional guests without anyone being turned away and without anyone losing their room. The total number of guests has doubled, and the hotel is still full. What Hilbert's hotel is demonstrating is not a trick or a clever puzzle. It is a genuine feature of how infinite sets behave, one that mathematicians had to come to terms with in the 19th and early 20th centuries, and that many of them found deeply uncomfortable. Georg Cantor, who developed the mathematics of infinite sets, was attacked by colleagues who believed his results were absurd or even dangerous. Cantor himself had a difficult relationship with his own discoveries. And what Hilbert's hotel makes vivid is one of the central reasons why. For finite numbers, more is more. Add guests to a full hotel, and you have a problem. But for infinite sets, adding to them does not necessarily make them larger in any meaningful sense, because the concept of size itself behaves differently when you leave the finite world behind. The set of all positive integers and the set of all even positive integers are, in the relevant mathematical sense, the same size. Not approximately the same size, exactly the same size, even though the second set seems to contain only half the numbers of the first, because you can pair them up perfectly, 1 to 1, each positive integer with its double, with nothing left over. Mathematicians call two sets the same size if you can put them in a perfect 1-to-1 correspondence. And by this definition, the infinite natural numbers and the infinite even numbers are the same size. The infinite hotel full of guests and the same hotel with one more guest are the same size. The infinite hotel full of guests and the hotel with infinitely many more guests are still the same size. This equality of infinite sets is so strange that even mathematicians who work with it regularly say it requires a kind of mental adjustment. Your intuition, built from a lifetime of experience with finite quantities, keeps generating the wrong answer. You keep feeling like adding guests to a full hotel should be impossible. The feeling is accurate for every hotel you have ever stayed in or could ever stay in. It is simply wrong for Hilbert's hotel. And Hilbert's hotel is not a hotel. It is a picture of what infinite sets are actually like. When you try to reason about infinity using the tools you developed for thinking about finite things, you get the wrong answers. Infinity is not a very large number. It is something categorically different. Something that follows different rules, something that resists every analogy drawn from ordinary experience. What makes Hilbert's hotel particularly interesting is not just that it shows you can add guests to a full infinite hotel. It shows that you can do this in infinitely many different ways, each of which produces a situation that looks different, but is, in the relevant mathematical sense, identical to the original. You keep arriving at the same infinity, no matter how much you add to it, as long as what you are adding is countably infinite. Cantor proved that not all infinities are the same size. Some infinities are genuinely larger than others. The real numbers between 0 and 1, for example, cannot be put in one-to-one correspondence with the natural numbers, no matter how clever your pairing scheme. There are strictly more of them. Cantor's proof of this is one of the most beautiful and disturbing arguments in mathematics, and it points to something that Hilbert's hotel cannot accommodate. No matter how cleverly the manager shuffles guests around, he cannot fit the real numbers into his hotel. They are too many, even for a hotel with infinitely many rooms. So there are infinities that Hilbert's hotel can handle, and infinities that it cannot. The hotel, full of countably infinite guests, is a specific kind of infinite structure, and it is genuinely smaller than other infinite structures that mathematics describes. Infinity, it turns out, is not a single thing. It is a hierarchy, and Hilbert's hotel sits near the bottom of that hierarchy, large beyond any finite comprehension, and yet dwarfed by what lies above it. If you were a guest in Hilbert's hotel, and the manager asked you to keep moving to make room for more guests, how far would you have to travel before you reached a room that no one had occupied before? And what does it mean that the answer is that you never would? There is one more feature of Hilbert's hotel worth sitting with before leaving it. The hotel can also lose guests in ways that seem paradoxical. Suppose every guest in an odd-numbered room checks out simultaneously. An infinite number of guests leave. The hotel is now half empty in some intuitive sense, with all the odd rooms vacant. And yet the hotel still has infinitely many guests, all the guests in even-numbered rooms. An infinite departure has left the hotel still infinitely occupied. Now suppose every guest from room 3 onward checks out. An infinite number of guests leave. What remains? Guests in rooms 1 and 2. 2 guests. An infinite hotel that was full now has 2 occupants after an infinite departure. Both departures involved infinitely many guests leaving. One left the hotel infinitely occupied. One left it with 2 guests. How can the same quantity of departures produce such different results? Because the quantity of departures is not what determines the outcome. What matters is which guests left, which rooms they vacated, and whether the remaining guests form a finite or infinite set. Subtraction does not work cleanly with infinite quantities. You can subtract infinity from infinity and get infinity. The result depends entirely on the specific infinite sets involved, not on the abstract quantity being subtracted. This is why mathematicians say that infinity minus infinity is indeterminate, not because they do not know the answer, but because the answer depends on context in a way that finite arithmetic never does. Finite subtraction always gives a unique result. Infinite subtraction is a different kind of operation entirely, one that requires you to know the structure of what you are working with, not just its size. Hilbert's hotel holds all of this in a form you can almost picture. A corridor stretching away into the dark, room after room after room, lights on in every one of them. The manager at the desk with his phone, ready to shuffle everyone around at a moment's notice. And somewhere far down that corridor, in a room with a number too large to write out, a guest who has never had a neighbor 2 doors to the right, because those rooms keep appearing as fast as they can be needed. What would it feel like to be the guest in room infinity, if such a room could exist? And would you know you were there? Thomson's lamp. At noon, a lamp is switched on. After half a minute, it is switched off. After a quarter of a minute more, it is switched on again. After an eighth of a minute, off again. After a 16th, on. The switching continues, each interval exactly half the length of the previous one. After 2 minutes of this, all the switching is complete. An infinite number of switches have been flipped in a finite amount of time. Now the question. At exactly 2 minutes, is the lamp on or off? James Thomson, the philosopher who invented this thought experiment in 1954, was pointing at something that feels like it should have a straightforward answer. The lamp was switched an infinite number of times. Each switch alternated its state. So the lamp is, what? On if the last switch turned it on, off if the last switch turned it off. But there was no last switch. The sequence of switches has no final term. There is no switch that came last, because after every switch, there was always another one, half as long away. You cannot say the lamp is on, because you could point to an infinite subsequence of times where it was off. You cannot say it is off, because you could point to an infinite subsequence where it was on. You cannot say it is in some intermediate state, because lamps do not have intermediate states. They are either on or off. And you cannot say the question has no answer, because at 2 minutes the lamp exists and must be in some state. Thomson used this to argue against the possibility of what philosophers and mathematicians call supertasks, tasks that involve completing an infinite number of steps in a finite amount of time. His argument was that if supertasks were possible, they would lead to situations like this one, where a perfectly well-defined physical setup leads to a question with no coherent answer. And since questions about the state of a lamp must have answers, supertasks must not be possible. The counter-argument came fairly quickly. Mathematicians pointed out that Thomson's lamp does not actually show that supertasks are impossible. It shows that the infinite sequence of switching operations does not, by itself, determine the state of the lamp at the completion point. The mathematical series describing the switching converges. The total time adds up to exactly 2 minutes, but the series of lamp states does not converge to any particular value. On-off, 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 oscillating forever faster and faster, approaching but never settling. What this means, mathematically, is that the problem is underspecified. The switching operations tell you everything about the lamp's state at every moment before 2 minutes. They tell you nothing about its state at 2 minutes. To know what state the lamp is in at exactly 2 minutes, you would need additional information, an initial condition for the completion point, something that specifies what happens when the infinite sequence terminates. Some philosophers find this resolution unsatisfying. The lamp is a physical object. Physical objects have states. Something must determine the state of the lamp at 2 minutes, even if the switching sequence does not. The question is not what the mathematics says, but what reality would actually produce. And reality, being physical and causal, presumably has some answer to the question. But here is what makes this genuinely strange. No physical process we know of would actually produce Thomson's lamp. Real switches have finite switching times. Real circuits have resistance. Real lamps have thermal inertia. As the switching intervals shrink towards zero, something in the physical setup would break down long before the infinite switching was complete. The scenario is physically impossible not just in practice, but in principle, because quantum mechanics and the finite speed of physical processes put a lower bound on how quickly a switch can be meaningfully toggled. So Thomson's lamp is not a physical paradox, it is a mathematical one. It exists in the idealized world, where physical constraints have been removed and pure mathematical operations are permitted. In that world, it reveals a genuine gap between what infinite sequences can describe and what states of affairs they can determine. This gap appears in other places in mathematics too. You can define a function on every rational number in an interval, but that function's behavior at irrational numbers in the same interval is not determined by its values at the rationals. You can describe what happens at every moment before 2 minutes, and the description is complete for all those moments, but it leaves the moment at exactly 2 minutes unspecified. Mathematicians are comfortable with this kind of thing. They are used to the idea that a function defined everywhere on a dense set does not thereby have a value everywhere. But the lamp is not a function. It is, in the thought experiment at least, a physical object. And physical objects are supposed to have definite states whether or not any mathematical description determines those states. Whether the lamp is on or off at 2 minutes is, in some sense, the question of whether physical reality follows mathematical descriptions or whether it has an existence that goes beyond what mathematics can capture. Most physicists would say the question is ill-posed because the scenario is physically impossible. Most mathematicians would say the question has no answer because the series does not converge to a state. And Thomson, who started it all, would probably say both of those responses confirm his point. The lamp sits on the table at 2 minutes, somewhere between on and off, in a state that no process that preceded it determines, and the question of what that state is may be one of those questions that is genuinely unanswerable, not because we lack information, but because the concept of answer does not apply. If you could be at the lamp at exactly 2 minutes, watching it, what do you think you would see? And does your answer tell you something about whether you believe physics or mathematics is the more fundamental description of what is real? There is a version of Thomson's lamp that appears in human experience without any physics or mathematics, and it has a similar structure of infinite approach toward a moment that never quite arrives with a determinate answer. Consider the experience of trying to make a decision you keep putting off. Not because you do not have enough information, but because the structure of the deliberation is such that each consideration prompts a counter-consideration. Each reason for generates a reason against. Each resolution generates a new doubt, and the intervals between these oscillations grow shorter and shorter as the decision point approaches. You go back and forth faster and faster, the switching between yes and no becoming more rapid, and when the moment of decision finally arrives, you are not sure what you decided. You find yourself having done something, committed to something, without a clear sense of when the deciding happened. The Thomson's lamp structure is present, an infinite number of mental switches in a finite span of approaching time. And at the moment of commitment, the state of your decision is not determined by any single switch or by the sequence as a whole. Something else determines it, the specific physical state of your brain at that moment, the specific circumstances that made one option available and the other suddenly less so, something external that tilted the oscillation into stillness. In the thought experiment, there is no such external factor. The lamp switches according to the rule and nothing else. In real human deliberation, there is always something else. The phone call that comes at just the right moment, the friend who says the thing that somehow settles it. The arbitrary fact that one option happens to be slightly more immediately available when the oscillation finally runs out of time. Thomson's lamp, in this reading, is not just a puzzle about physics and mathematics. It is a puzzle about whether infinite processes ever resolve themselves, or whether resolution always requires something from outside the process. In mathematics, sometimes they do resolve, when the series converges. Sometimes they do not, when it oscillates. In human life, resolution always seems to come from outside, from the world pressing in, from something that interrupts the oscillation before it can complete its infinite run. What decision in your life has had this oscillating structure? And what was the thing that finally stopped the switching? Not by resolving it, but by simply making it stop. One last thing. The impossibility of Thomson's lamp in physical reality might not be a limitation of our technology. It might be a structural feature of how the universe works, reality refusing to generate situations that have no coherent answer. Or it might just be that switches have mass and quantum limits, and the thought experiment was never pointing at anything real. Both feel like answers. Neither feels complete. Cantor's diagonal argument. Georg Cantor wanted to know how big infinity was, not in a vague poetic sense, but in a precise mathematical sense. He wanted to know whether all infinite collections were the same size, or whether some were genuinely larger than others. And in 1891 he published a proof so elegant and so disturbing that it changed mathematics forever. He started with the real numbers, all the decimal numbers that exist between 0 and 1, not just the fractions, not just the nice terminating decimals, but every possible infinite decimal expansion. Numbers like 0.3333 going on forever. Numbers like pi-3, which begins 0.14159 and continues without pattern or repetition. Numbers like completely random infinite strings of digits that have no formula and no pattern at all. Cantor asked whether these numbers could be listed. Could you write them in a sequence, first one, second one, third one, and so on, such that every real number between 0 and 1 appeared somewhere on the list? Maybe not in any obvious order, maybe not in any order you could describe concisely, but just some sequence, however arbitrary, that managed to include all of them. He proved that you cannot. No matter what list you make, no matter how clever your ordering scheme, there will always be real numbers between 0 and 1 that your list missed. The real numbers are too many to be listed. They are a larger infinity than the counting numbers. Here is how the proof works, and it is worth following carefully because it is one of the most beautiful arguments in mathematics. Suppose someone hands you a list. They claim it contains every real number between 0 and 1. The list looks like this. First number, some infinite decimal. Second number, another infinite decimal. Third number, another. And so on, down the page forever. Now Cantor constructs a new number using only the diagonal of this list. He looks at the first digit after the decimal point of the first number on the list. He changes it. If it is a 3, he writes a 4. If it is anything else, he writes a 3. He looks at the second digit of the second number. He changes it the same way. He looks at the third digit of the third number, changes it. He continues forever down the diagonal. The number he has constructed differs from the first number on the list in its first digit, differs from the second number in its second digit, differs from the third number in its third digit, differs from every number on the list in at least one digit, which means the number he constructed is not on the list. But the list was supposed to contain all real numbers between 0 and 1. Contradiction. Whatever list you provide, Cantor can construct a real number that is not on it. Not because the list is short, not because you made a mistake, but because the structure of real numbers is such that any attempt to list them will always miss some. The real numbers are uncountably infinite, which means they are a strictly larger infinity than the countable infinity of the natural numbers. When Cantor published this, the reaction from some mathematicians was fierce. Leopold Kronecker, one of the leading mathematicians of the time, called Cantor a corrupter of youth. Henri Poincaré called Cantor's set theory a disease from which mathematics would one day recover. The objections were partly professional and partly philosophical. Many mathematicians felt that completed infinities, the idea of treating an infinite set as a finished object you could compare to other objects, was incoherent or even immoral. Mathematics, they felt, was about constructing things step by step, not about reasoning about completed infinite collections. Cantor defended his work with increasing desperation. He suffered from depression throughout his career, partly from the attacks and partly from his own struggle with the implications of his results. He spent years trying to resolve what he called the Continuum hypothesis, the question of whether there was any infinity between the countable infinity of the natural numbers and the uncountable infinity of the natural numbers and the uncountable infinity of the real numbers. He could not prove it either way. It turned out later that the question cannot be resolved within standard mathematics, a result proved by Kurt Gödel and Paul Cohen in the 20th century. What the diagonal argument reveals is something that sounds modest, but is actually quite strange. Not all infinities are equal. Some infinite sets are larger than others, in a precise and provable sense. The real numbers cannot be matched up one-to-one with the natural numbers because there are simply more of them. Not in some vague sense, but in the specific sense that any attempted matching will always leave real numbers unmatched. And the argument that proves this is not complicated. A child who understood lists and decimal numbers could follow it. The proof is almost offensively simple for something so profound. Assume you have a list. Look at the diagonal. Change each digit. The new number is not on the list. Done. The uncountability of the real numbers, one of the most important facts in all of mathematics, follows from a construction you can explain in 5 minutes. What is strange is that the construction is so mechanical. You do not need to understand anything deep about the real numbers to run it. You just need to be able to look at diagonals and change digits. And yet from this mechanical procedure emerges a fact about the size of infinity that resisted mathematical understanding for centuries. Cantor's diagonal argument is one of those rare things in mathematics where the proof and the result feel completely incommensurate. The proof is so simple, the result is so enormous. And somewhere in that gap between the two is where the strangeness of infinity lives. If someone handed you a list claiming to contain every real number between 0 and 1, what would you feel as you ran through Cantor's diagonal and constructed the number that was not on it? Not intellectually. What would you feel? There is a version of the diagonal argument that applies not to numbers, but to descriptions, and it produces a result that is just as strange as the original. Consider all the things you could say about the world. Every sentence, every description, every theory, every story. If language is built from a finite alphabet and sentences have finite length, then the set of all possible sentences is countably infinite. You could list them all in principle, in some order. Now consider all the possible ways the world could be. All possible physical configurations of all matter and energy. All possible histories, all possible futures, all possible arrangements of all possible things, the space of possible worlds. Is the space of possible worlds countable? Can you list every possible way things could be, in some sequence, and include all of them? Cantor's argument suggests the answer might be no. The space of possible worlds might be uncountably infinite, too large to be captured by any list of descriptions, even an infinite list, which would mean that language, even an infinitely extended language, cannot describe every possible way things could be. There would always be possible worlds that fall through the gaps between descriptions, that no finite sentence in any language could pick out precisely. Whether this is a real feature of reality or just a feature of how description and mathematics interact is genuinely contested. But it suggests that the gap between what can be described and what can exist might be as real and as large as the gap Cantor found between the countable and the uncountable. Some things exist beyond the reach of description, not because they are too complex or too subtle or too large, but because the structure of description is countable and the structure of possibility might not be. What would it mean to be one of those things? Something real, something possible, but something no description in any language could ever fully reach. One more dimension worth noting. The proof does not just show that real numbers are uncountable. It shows that uncountability survives every attempt to overcome it. No matter how clever your list, Cantor's procedure constructs a number not on it. You add that number. Cantor constructs another one missing from the new list. The procedure never fails because it does not depend on any specific feature of your list. It works on every possible list, not just the ones you happen to try. You cannot escape it by being cleverer. Cleverness is irrelevant. And what that means is that some infinities are genuinely irreducibly larger than others, not in a fuzzy intuitive sense, but in a precise, proven, inescapable sense, established by nothing more than the ability to look at a diagonal and change a digit. Simple enough to explain in minutes, large enough to contain a fact that took centuries to find, and strange enough that even the person who proved it was not entirely at peace with what he had found. Galileo's paradox. Galileo Galilei noticed something strange about numbers that he could not quite explain and that he wrote about in his final book, published in 1638 while he was under house arrest. The observation is simple enough to state in a sentence. There seem to be both fewer perfect squares than natural numbers and just as many. The natural numbers are the counting numbers, 1, 2, 3, 4, 5, and so on forever. The perfect squares are the numbers that are the square of some natural number, 1, 4, 9, 16, 25, and so on. The squares are clearly a subset of the natural numbers. Every perfect square is a natural number, but not every natural number is a perfect square. Between 1 and 10, there are 10 natural numbers, but only 3 perfect squares. Between 1 and 100, there are 100 natural numbers, but only 10 perfect squares. The further you go, the more thinly scattered the squares become relative to the naturals. Intuitively, there are far fewer squares than there are natural numbers, and yet you can match them up perfectly, 1 to 1, with nothing left over. Pair 1 with 1, pair 2 with 4, pair 3 with 9, pair 4 with 16. Every natural number gets paired with its square, and every square gets paired with exactly one natural number. The pairing is perfect and exhaustive. No natural number is left unpaired. No square is left unpaired. By the matching criterion, which is how mathematicians define two sets having the same size, the natural numbers and the perfect squares are the same size, but by the subset criterion, the perfect squares are a proper part of the natural numbers and therefore smaller. Both arguments seem valid. Both cannot be correct simultaneously. Galileo did not know how to resolve this. He concluded, reasonably enough for his time, that the concepts of greater, equal, and less simply did not apply to infinite quantities. Infinity was a different kind of thing, and the ordinary rules of comparison broke down when applied to it. He left the question open. 2 centuries later, Georg Cantor gave what has become the accepted resolution, though it is a resolution that many people find less satisfying than it sounds. Cantor defined the size of a set in terms of 1-to-1 matchings, rather than in terms of the subset relation. 2 sets are the same size, if and only if you can match their elements perfectly with nothing left over. By this definition, the natural numbers and the perfect squares are the same size. The subset relation, the intuition that part is smaller than whole, simply does not hold for infinite sets. This is a genuine mathematical choice. Cantor chose to privilege the matching criterion over the subset criterion as the definition of same size, and this choice is mathematically productive. It led to his discoveries about different sizes of infinity and to an enormous body of mathematics that has proven itself by generating useful and consistent results. But the choice is still a choice. You could, if you wanted to, define the size of infinite sets in terms of the subset relation. On that definition, the natural numbers would be strictly larger than the perfect squares. The mathematics that followed from this choice would be different, and, as far as we know, less rich and useful. But it would not be obviously wrong. What Galileo's paradox reveals is that when you move from the finite world to the infinite one, the ordinary concept of size does not have a uniquely correct extension. Size, for finite sets, is unambiguous. For infinite sets, you have to make a choice about what you mean, and different choices produce different mathematics. The mathematics we have chosen, the one where natural numbers and perfect squares are the same size, is the dominant one because it works better. But the intuition that drove Galileo's discomfort, the sense that part should be smaller than whole, is not simply wrong. It is the residue of a concept that was never designed to handle infinity. What makes Galileo's paradox interesting to sit with is that it surfaces a conflict between two things that are both obviously right in the finite world. Parts are smaller than wholes. Things that can be matched up are the same size. In the finite world, these never conflict. In the infinite world, they do, consistently and irreparably. And the only way to do mathematics is to choose one and abandon the other, whether that counts as resolving the paradox or just deciding which horn of it to live with, is a question worth thinking about more carefully than most treatments of this topic do. Count the natural numbers, count the squares. Both counts run forever, both counts never end, and yet one of them only visits numbers that come up in the other list and comes up far less often. What does it mean for two things to be the same size if one of them contains the other as a proper part? And is the answer to that question a mathematical fact or a decision about what mathematics should mean? There is a version of this that appears in everyday thinking about fairness and equality, and it has the same structure as Galileo's mathematical observation. Consider the question of whether two groups are being treated equally. You could define equal treatment in terms of the matching criterion. If every person in Group A receives a counterpart in Group B who is treated the same way, and vice versa, then the groups are treated equally. Or you could define it in terms of the subset criterion. If Group A receives only things that Group B also receives, but Group B receives additional things, then Group B is treated better. In finite contexts, these two definitions agree. In infinite or very large contexts, or in contexts where the categories get complicated, they can come apart in ways that produce genuine disagreements about whether equality has been achieved. The argument about whether identical matching constitutes equality, or whether systematic differences in what each group receives constitute inequality, shows up in political philosophy, legal theory, and everyday moral reasoning. And people on different sides of these arguments are often not disagreeing about facts. They are disagreeing about which concept of sameness is the right one to apply. Galileo's paradox makes this visible in a clean mathematical setting where all the facts are agreed upon. Both groups agree that the squares are a subset of the naturals. Both groups agree that you can match them perfectly. The disagreement is about what same size means, and that disagreement does not have a mathematical answer. It has a choice. Most real disputes about equality have a similar structure underneath the factual disagreements. Not just a dispute about what the facts are, but a dispute about which concept of equality is the operative one. And that dispute cannot always be resolved by gathering more facts. What would it change about a disagreement you are in, or have been in, if you recognized that part of what is contested is not a fact, but a definition? And is a definition the kind of thing that can be right or wrong, or only more or less useful? There is one more thing Galileo's paradox reveals that is worth noting before leaving it. The paradox only generates a conflict because we are applying concepts developed for finite collections to an infinite one. The concept of size, as humans developed it, was built from experience with finite things. Rocks in a pile, animals in a field, people in a room. In all those contexts, part is always smaller than whole, and things that match up are always the same size, because in all those contexts, these two criteria agree. Moving to infinity, we took those concepts with us and found that they disagree. And the lesson might not be that we need to choose between them. The lesson might be that the concept of size, as we originally understood it, simply does not apply to infinite sets. It is like asking whether the color blue is heavier than the color red. The question has the right grammatical structure, but is asking something that the concepts involved were not designed to answer. Cantor chose to extend the matching criterion and call it size. That extension is enormously useful. But calling it size might be borrowing a word to mean something new, a new concept that only resembles the old one from a distance. Whether you think of that as resolving the paradox or as renaming it is perhaps another choice. Galileo wrote about this in his last book, The Discourses, published when he was nearly blind and confined to his home. He was a man who had spent his life measuring and counting things, and he ended it confronting a case where measurement generated a result he could not accept and could not refute. He decided infinity was simply beyond the reach of the concepts he had used all his life. He may have been wrong about the resolution, but he was honest about the discomfort. And honesty about discomfort is more useful than a resolution that papers it over. What does it tell you that a concept as basic as same size can break down so completely when pushed from finite to infinite? And what other basic concepts might be waiting to break down in similar ways when pushed into territory they were never built for? The Ross-Littlewood Paradox. At 1 minute before noon, you place 10 balls in a vase and remove ball number 1. At half a minute before noon, you place 10 more balls in the vase and remove ball number 11. At a quarter minute before noon, you place 10 more balls and remove ball number 21. This continues, each step taking half the time of the previous one, so that infinitely many steps are completed before noon arrives. How many balls are in the vase at noon? Most people, looking at this setup, say the vase must contain infinitely many balls. At each step you add 10 and remove 1. So the vase grows by 9 balls per step. After 100 steps you have 900 balls. After 1,000 steps 9,000. The number of balls grows without bound, so at noon, when infinitely many steps have completed, the vase should contain infinitely many balls. But wait. Label each ball with a number. The first 10 balls are labeled 1 through 10. The next 10 are labeled 11 through 20. And so on. At each step, the ball you remove is the lowest numbered ball currently in the vase. Ball 1 is removed in the first step, ball 11 is removed in the second step, ball 21 in the third, and so on. Now ask a different question. Is ball number 1 in the vase at noon? No, it was removed in the first step. Is ball number 2 in the vase at noon? No, it was removed in the second step. Wait, the second step removed ball 11, not ball 2. So when was ball 2 removed? Ball 2 was removed in the second step. Actually, let me track this more carefully. Step 1 removes ball 1. Step 2 removes ball 11. Step 3 removes ball 21. Step 10 removes ball 91. Ball 2 is not removed in any of these steps. When does ball 2 get removed? Ball 2 gets removed in some step where it is the lowest numbered ball in the vase. But balls 1 through 10 were placed in step 1. Ball 1 was removed in step 1. So after step 1, balls 2 through 10 remain, plus whatever was added later. Ball 11 is removed in step 2, ball 2 is still there. Ball 21 in step 3, ball 2 is still there. Following the pattern, ball n gets removed in step n, ball 2 gets removed in step 2, but step 2 removes ball 11. This is where the paradox bites. Under the rule as stated, the ball removed at each step is the ball with the smallest number currently in the vase. After step 1, the smallest numbered ball in the vase is ball 2. Step 2 should remove ball 2, not ball 11. Which version of the problem is being described depends on how you specify the removal rule. If you remove the lowest numbered ball each step, then every ball eventually gets removed, the vase is empty at noon, and the answer is 0. If you remove ball 10 times n-9 at step n, following the pattern 1, 11, 21, some balls are never removed, and the vase contains infinitely many balls. Same physical description, 2 different answers depending on the removal rule, and the 2 removal rules seem, at first glance, to be the same thing. This is the Ross-Littlewood Paradox, named after Sheldon Ross and J.E. Littlewood, who studied versions of it. What it shows is that the result of an infinite process can depend entirely on the order in which operations are performed, and that seemingly equivalent descriptions of the same process can lead to radically different outcomes when taken to infinity. For finite processes, this does not happen. If you add 10 things and remove 1 from a pile, the pile has 9 more things than it started with, regardless of which thing you removed. The result does not depend on labeling or ordering, but for infinite processes, these things matter enormously. The specific structure of which operations happen when, and which objects are affected, determines the outcome in ways that cannot be reduced to a simple count of how many things were added and removed. This is related to the mathematical phenomenon of conditional convergence in series. The German mathematician Bernhard Riemann proved that if an infinite series converges conditionally, meaning it converges but does not converge absolutely, you can rearrange its terms to make it sum to any value you like, or to diverge. The same series of numbers, rearranged, can equal any number. This is the Riemann rearrangement theorem, and it is deeply counterintuitive. Addition, which seems like a commutative and associative operation, turns out to depend on order when you are adding infinitely many terms. Ross-Littlewood is the physical version of this mathematical phenomenon. The balls are the terms, the order of operations is the rearrangement, and the answer, 0 or infinity, corresponds to the different sums you can get by rearranging a conditionally convergent series. What the paradox reveals is something that finite intuition completely fails to prepare you for. Order matters, infinitely, when you are dealing with infinite processes, not slightly more than in finite cases, infinitely more. Changing the order can change the answer from 0 to infinity. And the unsettling part is that the two descriptions, remove the lowest numbered ball and remove ball 10 times n-9, sound like they should describe the same process. The discrepancy only becomes visible when you check which specific balls are removed at each step, which is exactly the kind of detail that seems irrelevant for finite processes and turns out to be everything for infinite ones. If someone told you a process that added more than it removed at every single step had produced an empty result at the end, how would you know whether to believe them? And what would you need to check to be sure? There is a version of the Ross-Littlewood Paradox that appears in human memory and narrative, and it has the same disturbing structure of order, mattering infinitely. Your memory of a period of your life is not a simple count of good and bad experiences. It is a sequence of experiences in a specific order, and the order shapes what the period feels like in retrospect, in ways that go far beyond the sum of individual moments. Psychological research on memory, particularly work by Daniel Kahneman, has shown that how an experience ends matters disproportionately to how we remember the whole. A painful medical procedure remembered as ending with a period of mild discomfort is rated less negatively than one of shorter duration that ended at peak pain. The total amount of pain experienced is not what determines the remembered experience. The order and endpoint do. This is the Ross-Littlewood phenomenon in human memory. Two sequences of experiences with the same total content can produce radically different remembered outcomes depending on their structure and order, and just as with the balls, the difference is not visible if you just count the moments. You have to track which specific experiences came when, and what order they appeared in, to predict what the person will remember. People sometimes try to save a relationship, a project, or a period of their life by making the ending good, recognizing intuitively that the end matters more than the middle. This is not irrational. It is a recognition of the Ross-Littlewood structure of memory. The same collection of experiences, differently ordered, produces a different memory. The ending has a weight that the middle does not because it contains more, but because of where it sits in the sequence. Whether this means you should engineer endings, or whether it is a bias in memory that distorts your perception of what actually happened, is a question the paradox raises without answering. What experience in your life would you feel differently about if the order of events within it had been different, even if the total content had been identical? And does the fact that order matters that much tell you something about what memory is actually tracking? One last thing the Ross-Littlewood Paradox makes visible: when people argue about whether a long-term process has been net positive or net negative, they are often not just disagreeing about the count of good and bad things that happened. They are disagreeing about the order, the structure, which things came when, what the trajectory looked like. Two people can look at the same sequence of events and reach opposite conclusions about whether the overall result was good, not because they are counting differently, but because different structural features of the sequence are salient to each of them. Understanding the paradox does not resolve those disagreements, but it does clarify what kind of disagreement they are. Not a factual dispute about what happened, a structural dispute about which features of the infinite sequence of events are the ones that determine the answer. And in human affairs, unlike in mathematics, there may not be a fact of the matter about which structural features are the correct ones to privilege. The answer might genuinely depend on how you look at it. Grandi's series. Take the number 1, subtract 1, add 1, subtract 1. Keep going forever. 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1 extending out to infinity. What is the sum? If you stop after an even number of terms, the sum is 0. 1 minus 1 is 0. 1 minus 1 plus 1 minus 1 is 0. Every time you pair off the terms, they cancel. If you stop after an odd number of terms, the sum is 1. 1 is 1. 1 minus 1 plus 1 is 1. The unpaired term at the end gives you 1. The series oscillates. It never settles. There is no point where the partial sums converge to a stable value. In the standard mathematical sense, the series diverges. It does not have a sum, and yet Guido Grandi, an Italian monk and mathematician, calculated its sum in 1703 and arrived at the answer 1/2. Here is how. Call the sum S. Then S equals 1 minus 1 plus 1 minus 1 and so on. Factor out the terms starting from the second one. S equals 1 minus the quantity 1 minus 1 plus 1 minus 1 and so on. But that quantity in the parentheses is just S again, so S equals 1 minus S. Solve for S. 2S equals 1, so S equals 1/2. Leibniz found this result and thought it was correct, arguing that 1/2 was a kind of average between 0 and 1, the two values the partial sums oscillate between. Other mathematicians of the era found different arguments for 1/2, including summing the series in different ways. The 19th century brought more careful analysis and the conclusion that divergent series simply do not have sums in the standard sense. Grandi's series was classified as a series that diverges and has no sum. End of story. Except it was not the end of the story. In the 20th century, mathematicians studying physics and number theory found that divergent series, including Grandi's, had well-defined values in certain generalized summation methods. Cesaro summation, Abel summation, Ramanujan summation, all of these assign a value of 1/2 to Grandi's series. And these are not arbitrary choices. These summation methods satisfy natural axioms and produce consistent and useful results in contexts where standard summation fails. The sum of all positive integers, 1 plus 2 plus 3 plus 4 going on forever, is assigned the value -1/12 under these methods. String theory uses this result. Euler calculated it using formal manipulations and arrived at the same answer. The mathematics is coherent, and it is used in real physics that produces real predictions that match real observations. So what is going on? Are Grandi's series and the sum of all positive integers meaningful quantities or not? Do they have sums or don't they? The answer depends on what you mean by sum. Standard summation, the kind defined through limits of partial sums, says no. These series diverge and have no sum. Generalized summation methods, developed specifically to handle divergent series in a principled way, say yes, and they assign specific values. The question of which answer is correct is really the question of which concept of sum is the right one for the context. What Grandi's series reveals is that the concept of sum is not a single thing. For finite collections, addition is unambiguous. For infinite series, it is not. The ordinary limit-based definition of sum is one possible extension of finite addition to the infinite case. It is the most natural extension for most purposes. But it is not the only extension, and for some purposes other extensions are more useful. This mirrors what happened with size in Galileo's paradox. Size, for finite sets, is unambiguous. For infinite sets, you have to make a choice. Sum, for finite collections, is unambiguous. For divergent infinite series, you have to make a choice. And the choices available are not arbitrary. Each has properties that make it natural for specific purposes. The discomfort Grandi's series creates comes from the collision between the expectation that mathematical questions have definite answers and the reality that some mathematical concepts have multiple valid extensions when pushed beyond their original domain. Whether 1/2 is the sum of Grandi's series is not a question with a yes or no answer. It is a question that requires you to specify what you mean by sum. And once you specify that, the answer is determinate. But the specification is yours to make, and different reasonable specifications give different answers. Grandi himself, who is a theologian as well as a mathematician, saw theological significance in the series. He believed the oscillation between 0 and 1, and the average value of 1/2, illustrated how God could create something from nothing, the series producing a value between existence and non-existence. Whether you find this persuasive is between you and your theology, but the mathematics is real. Grandi's series has a sum of 1/2 in contexts where that value is useful and consistent, and no sum in contexts where the standard definition is required. Both statements are true, and the coexistence of both truths is what makes the series philosophically interesting rather than just mathematically convenient. What would it change about your confidence in mathematical results if you knew that even something as basic as whether a series has a sum depends on which framework you are working in? And is that dependence a limitation of mathematics, or just an honest description of how concepts work when pushed beyond where they were designed to go? There is a physical version of Grandi's series that is worth describing because it makes the abstraction concrete in a way that the pure mathematics does not. Imagine a ball that bounces. Each bounce takes exactly half the time of the previous one. After an infinite number of bounces, all completed in a finite total time, is the ball in the air or on the ground? By the same argument as Thomson's lamp, the answer is indeterminate. The ball is alternately in the air and on the ground with each bounce. The bounce is coming faster and faster, and at the completion point, the sequence of positions oscillates without settling. Just like Grandi's series, which alternates between 1 and 0, the ball alternates between two states without converging. The regularized value of 1/2, if you could give it physical meaning, might correspond to some average state between air and ground. This is physically meaningless for a ball, but in quantum mechanics something similar actually happens. Quantum systems can exist in superpositions of states, and the expectation value of a quantum observable can be a number that corresponds to neither of the definite values the system could be in when measured. The 1/2 of Grandi's series finds a home in physics, not as an actual position of a ball, but as the kind of intermediate value that quantum mechanics assigns to systems before measurement. Whether this is a coincidence or a deep connection between the mathematics of divergent series and the structure of quantum mechanics is something physicists and mathematicians are still working out. The connection is real enough to be useful. What it means is harder to say. What does it mean for a mathematical result that seems to make no physical sense to turn out to be physically meaningful in a context you did not anticipate? And does that say something about mathematics, or about physics, or about the relationship between them? Grandi himself would probably have been astonished to learn that his theological series turned out to be relevant to quantum field theory. He was pushing formal manipulations past the point where they were strictly justified, arriving at an answer that felt right before the justification existed. The formal understanding came 2 centuries later. The result came first, from intuition and a willingness to follow the algebra wherever it led. This is how a lot of mathematics works. The justification follows the discovery, and sometimes the discovery looks like nonsense until the right context arrives to make it meaningful. Grandi followed his series to 1/2. It took 200 years to understand why 1/2 was the right answer, and in what sense, and for what. The Tristram-Shandy Paradox. Tristram-Shandy is a character from an 18th century novel by Laurence Sterne. He is writing his autobiography. The project is going slowly. In fact, it is going so slowly that it takes him 2 years to write about the first 2 days of his life. At this rate, he reasons sadly, he will never catch up. As he writes, more life is happening, and the ratio of life lived to life written about will only get worse. The autobiography will always be falling further and further behind. Bertrand Russell, in his Principles of Mathematics, published in 1903, pointed out that Tristram-Shandy was wrong. Or rather, that Tristram-Shandy was only wrong because he was assuming a finite lifespan. If Tristram-Shandy lived forever, and if he continued writing at the same rate of 2 years to cover 2 days, then his autobiography would eventually cover his entire life. Here is why. In the first 2 years, he writes about days 1 and 2. In the next 2 years, he writes about days 5 and 6, and so on. Each pair of days gets written about, eventually. Day 1 gets covered in years 1 and 2. Day 365 gets covered eventually, in some specific pair of years far down the line. Any specific day you name will appear in the autobiography, provided Tristram-Shandy lives long enough and keeps writing. So if he lives forever, every day of his life gets covered. The autobiography is complete. Tristram-Shandy catches up. But here is the paradox. At any specific moment in time, Tristram-Shandy is always falling further behind. After 2 years, he has covered 2 days but lived 2 years. He is 730 days behind. After 4 years, he has covered 4 days but lived 4 years. He is 1456 days behind. The gap is growing, not shrinking. It grows forever, And yet, in some sense, the autobiography covers every day of his life. Russell was pointing at the same phenomenon Galileo noticed with the perfect squares. You can have a one-to-one pairing between two infinite sets, even when one of them seems to be falling constantly further behind the other. The natural numbers can be matched with the even numbers, despite the even numbers becoming increasingly sparse relative to the natural numbers as you go further out. What the Tristram-Shandy paradox adds to Galileo's observation is the temporal dimension. Galileo's paradox is about static sets. Tristram-Shandy is about a process unfolding in time, where at every moment the process seems to be losing, and yet in the limit it wins. This is a strange feature of infinite processes. The local behavior and the global behavior can be completely disconnected. At every step along the way, Tristram-Shandy is falling further behind. The gap grows without bound, and yet every specific day gets covered. The global outcome is that the autobiography is complete. The local behavior never suggests this outcome. You could watch the process for 1 trillion years, and nothing you see would suggest that the project will eventually succeed. This disconnect between local and global behavior appears throughout mathematics and physics. A sequence can converge to a limit even though the terms of the sequence bounce around and never seem to be approaching anything in particular. A function can be continuous even though zooming into any specific point makes it look erratic. The global structure can be smooth and regular, while the local structure is wild and apparently chaotic. In human terms, this translates to something about the relationship between what a process looks like while it is happening and what it looks like when you step back. A life that looks like constant failure at every local moment might, viewed from outside and from a sufficient distance, have a structure of progress that the person living it cannot see. Or it might not. The Tristram-Shandy paradox does not guarantee that every apparent local failure adds up to global success. It just shows that this is possible. That infinite processes can have global properties completely hidden from local observation. What the paradox does not resolve is whether Tristram-Shandy's infinity is realistic. Real human beings are finite. Real projects have deadlines. Real autobiographies do not get written over infinite lifetimes. The mathematical result is true and interesting, but its applicability to the original complaint that the autobiography will never catch up depends entirely on whether the relevant timescale is finite or infinite. Tristram-Shandy was sad because he assumed he would eventually die. Russell showed that if he did not die, the autobiography would be complete. But Tristram-Shandy is going to die. And so the original complaint stands, not as a mathematical error, but as a practical reality about finite lives and finite projects. The consolation the paradox offers is perhaps not that infinite projects succeed, but that the fact that something looks like it is falling further behind at every moment does not tell you anything reliable about whether it will ultimately succeed. Local failure is not evidence of global failure. The gap growing does not mean the gap never closes. Whether that is a mathematical curiosity or a genuinely useful thing to know about how projects and lives work is something the paradox leaves for you to decide. If you were Tristram-Shandy, writing 2 years about every 2 days, would you find Russell's consolation comforting? And does the answer depend on whether you believe you will live forever? There is a generalization of the Tristram-Shandy paradox that is worth exploring because it makes the same point more starkly. Suppose Tristram-Shandy writes very slowly, not 2 years per 2 days, but 2 years per 1 day. He takes twice as long to write about a day as to live it. Now is he falling further behind? Yes, faster than before. After 2 years he has written about 1 day and lived 2. The gap is worse. But suppose instead he takes 1,000,000 years to write about each day. Still a one-to-one correspondence. Day 1 gets covered in years 1 through 1,000,000. Day 2 gets covered in years 1,000,000, 1 through 2,000,000. Every specific day gets covered, eventually. The autobiography is complete over an infinite lifespan. Now suppose he takes as long to write about a day as there are atoms in the observable universe, some absurdly large finite number. Same conclusion. Every day gets covered. The autobiography completes. The rate at which he is falling behind does not matter, as long as the rate is finite. Even a finite rate that makes the gap grow by any fixed amount per unit time does not prevent every specific day from eventually being covered. As long as coverage of each day takes a finite amount of time, however large, every day gets covered in infinite time. What this means is that the Tristram-Shandy conclusion is extremely robust. It does not require the rate to be anything in particular. It only requires that the autobiography not take infinitely long to write about any single day. As long as each day has a finite, if perhaps astronomical writing time, the autobiography completes. And in reverse, the autobiography fails to complete if and only if some day requires infinitely long to write about. If every specific day can be written about in some finite time, however large, every day will eventually be written about. This is a surprisingly gentle condition, and it reveals how different infinite time is from finite time. Finite time is a race. Infinite time is not. Given infinite time, anything that can eventually be done will be done, regardless of how slowly it is proceeding at any particular moment. What project in your life might complete over an infinite timescale that looks hopelessly behind schedule on any timescale you can actually observe? And what does it mean to care about something that only succeeds in infinite time, if you are not going to have infinite time to see it? There is also a version of this that applies to forgetting rather than writing. A memory fades over time. Each recall strengthens it slightly, but recalls become less frequent. The gap between reinforcements grows. From your local perspective, the memory is always getting worse. And yet if your life went on long enough, you might recall it infinitely many times, infinitely many reconstructions of the same original experience. Whether that would preserve the memory or just produce infinitely many progressively distorted versions of it is a question the paradox raises without answering. Global completeness does not guarantee that what you have at the end resembles what you started with. Tristram Shandy's autobiography might cover every day, but each day is covered through a lens shaped by all the subsequent days not yet written about. Completeness and fidelity are different things, and the comfort of the infinite might not survive contact with what actually gets completed. The two envelopes paradox. Two envelopes sit in front of you. Someone tells you that one envelope contains exactly twice as much money as the other. You do not know which is which. You pick one and open it. You find $100 inside. Now you are offered a choice. Keep your $100 or switch to the other envelope. Should you switch? Most people say it does not matter. You have $100. The other envelope has either 50 or 200. 50% chance of each. Expected value of switching is half of 50 plus half of 200, which is 25 plus 100, which is 125. That is more than 100. So you should switch. But wait. The same argument applies before you open the envelope. Before seeing the amount, you know one envelope has twice what the other has. If you hold envelope A, then envelope B has either twice as much or half as much. Your expected gain from switching is positive, so you should switch before opening it. But then why open it at all? Before seeing anything, the logic says switch. After seeing the amount, the logic still says switch. No matter what you find inside, switching has higher expected value. But if you switch, you now hold the other envelope, and the same logic says switch back, and then switch again, and again, switching forever, never settling, never gaining anything. Something has gone wrong in the reasoning. The expected value calculation cannot be right if it always recommends switching regardless of what you find, because you cannot improve your situation by endlessly trading between two fixed envelopes. The flaw in the reasoning is subtle and has generated considerable philosophical discussion. The calculation treats the 50 and 200 as equally likely alternatives, given that you found 100. But this is not quite right. The probability that the other envelope contains 200 depends on the prior distribution over how much money was put in the envelopes in the first place. Here is what the calculation is secretly assuming. It is treating 100 as a value that could be the smaller amount, with the other envelope containing 200, or as the larger amount, with the other envelope containing 50. And it is treating these two cases as equally likely. But whether 100 is the smaller or larger amount depends on what the person filling the envelopes decided to put in. If they were equally likely to put in 50 100 as 100 200, then yes, both cases are equally likely. But if they put in a fixed amount and 100 happened to be what you found, the two cases might not be equally probable. The paradox dissolves when you specify the prior distribution. With most natural priors, the expected value calculation does not consistently favor switching. The problem with the naive calculation is that it uses a prior that is not actually valid. A prior that assumes you can treat your found amount as equally likely to be the smaller or larger, without specifying where the amounts came from. But there are prior distributions, unusual ones, under which the calculation does consistently favor switching regardless of what you find. These are called improper priors, distributions that do not actually integrate to one, that violate the basic requirements of probability. Under an improper prior, the paradox genuinely holds. The recommendation to always switch is mathematically consistent, and it is also useless, because you cannot act on it in any finite way. What the two envelopes paradox reveals is something about the relationship between probability and infinite possibilities. When the space of possibilities is finite, expected value calculations work cleanly and recommendations are actionable. When the space of possibilities is infinite, and especially when the possibilities extend without bound, expected value calculations can produce paradoxes. The sum of an infinite series of probability-weighted outcomes does not always converge, and when it does not, the expected value is undefined or paradoxical. This shows up in real decision theory. Whenever you are choosing between options where the potential outcomes are unbounded, expected value maximization can lead you astray. You might always be recommended to take a slightly worse option now for a slightly better expected future outcome in an endless chain that never resolves. The St. Petersburg paradox is the most famous version of this, but the two envelopes paradox is simpler and more immediate. The practical resolution for most people is that the envelopes contain specific finite amounts, the prior distribution is not improper, and the naive calculation is simply wrong in a specific diagnosable way. Switch or do not switch based on other considerations. Expected value, properly calculated with a valid prior, gives no consistent advice about which envelope to choose. But the fact that the naive calculation is so convincing and that it takes some work to see exactly where it fails is itself interesting. Probability theory is not as intuitive as it looks. The tools for reasoning about expected value and conditional probability, tools that seem like they should be mechanical and reliable, generate wrong answers when applied to infinite sample spaces without care. What would you do with the envelopes? Not what the calculation says. What would you actually do in the room with $100 in your hand and the other envelope sitting there? There is a version of the two envelopes paradox that operates in everyday decision-making without any envelopes or money, and it has the same structure of a calculation that seems to consistently recommend an action while actually providing no useful guidance. Consider the experience of comparing your current situation to an alternative. You have what you have. The alternative looks better in expectation, so you should switch. But once you have switched, your new situation is your current situation, and the original situation might look better in expectation from your new vantage point, so you should switch back. Every situation, viewed from outside, looks better than every situation viewed from inside. This is the two envelope structure applied to choices about how to live. The grass is always greener, not as a psychological bias, but as a mathematical property of certain ways of evaluating alternatives. If you consistently evaluate alternatives by comparing their expected value to your current situation, and if the comparison is made in a way that is systematically optimistic about the alternative, you will always prefer to switch and never be satisfied. The resolution is the same as in the original paradox. The consistent preference for the alternative is a sign that the evaluation method is flawed, not that every alternative is genuinely better. A valid comparison method, using a valid prior over what the alternatives actually contain, does not consistently favor switching. In practical terms, this means that if you find yourself always feeling that the alternative would be better, the problem might not be with your current situation. It might be with how you are generating alternatives and comparing them to what you have. You might be using an implicit prior that systematically distorts the comparison. What alternative to your current situation do you most consistently imagine to be better? And have you checked whether the comparison you are making is using a valid prior, or whether you are running a version of the two envelopes calculation that always produces the same recommendation regardless of what is in the envelope you are holding? One final thing about the two envelopes paradox that is worth noting: the paradox exists because the prior distribution over possible envelope contents is not specified. In the real world, distributions over possible outcomes are also often not specified, or are specified only implicitly through assumptions you have not examined. The two envelopes paradox is a reminder that when you do expected value calculations without being explicit about your prior, you are not doing neutral arithmetic. You are encoding assumptions that might be invalid. Making those assumptions explicit is often what turns a paradox into a problem with a solution. And making them explicit in your own life decisions might turn a persistent feeling that you should be doing something different into a clearer understanding of whether that feeling is tracking something real. The envelopes have specific amounts in them, your situation has specific properties. The calculation only goes wrong when you pretend the amounts or properties are drawn from a distribution you have not actually specified. Specify the distribution and the paradox dissolves. Whether you can always specify the distribution when it matters is a different question. Often it is not. And that gap matters. The harmonic series paradox. Add 1 plus a half plus a third plus a quarter plus a fifth. Keep going. Add a sixth, a seventh, an eighth, a ninth. Add the reciprocal of every positive integer. Forever. The terms are getting small. After 100 terms, each new term is less than 100th. After 1,000,000 terms, each new term is less than 1,000,000th. The terms are shrinking towards zero. Surely the sum must converge. Surely adding up smaller and smaller numbers will eventually reach some limit and stay there. But it does not. The harmonic series diverges. The sum grows without bound. Add enough terms and the sum will exceed 1,000,000,000,000,000,000. However large a number you specify, the harmonic series will eventually surpass it. This is not obvious. It is not even intuitively plausible for most people. The terms are becoming so small, so quickly. How can such tiny additions keep accumulating into something arbitrarily large? The proof is elegant and old. Nicole Oresme, a 14th century French philosopher and mathematician, proved it, making him one of the earliest people to demonstrate clearly that an infinite series of positive terms can diverge even when the terms approach zero. His argument groups the terms cleverly. Group the first term by itself, 1. Group the next two terms, 1/2 plus 1/3, which is more than 1/2 plus 1/4, which equals 1/2. Group the next four terms, 1/4 plus 1/5 plus 1/6 plus 1/7, which is more than 4 times 1/8, which equals 1/2. Group the next 8 terms similarly, getting more than 1/2. Each group of terms, however many you need to include, contributes more than 1/2 to the total. Since you can keep forming such groups indefinitely, adding more than 1/2 each time, the sum grows without bound. No matter how far out you go, you can always find enough additional terms to push the sum up by at least another half. The series diverges. What makes this counterintuitive is the conflict between two intuitions that both seem reliable. One says, if the terms approach zero, the sum must converge, because you are adding less and less each time. The other says, you are adding positive numbers, so the sum is always growing, and it never decreases. Both intuitions are true, but they do not together imply convergence. An infinite series can grow forever while adding less and less at each step. The condition for convergence is not that the terms approach zero. That is necessary but not sufficient. Many series with terms approaching zero diverge, like the harmonic series. The terms have to approach zero fast enough. The reciprocals of the squares, 1 plus 1/4 plus 1/9 plus 1/16, converge because the terms shrink fast enough. The reciprocals of the integers, the harmonic series, do not converge because the terms shrink too slowly. Where exactly is the boundary? The terms 1 over n to the power p converge for p greater than 1 and diverge for p equal to or less than 1. The harmonic series sits right at the boundary, with p equal to 1 on the diverging side. There is a physical analog to the harmonic series that is worth describing. Imagine you have infinitely many identical planks, each 1 unit long. Can you stack them at the edge of a table, each one overhanging the last, to extend as far out from the table as you like? Or does the stack inevitably fall? It turns out you can extend the stack arbitrarily far. The maximum overhang achievable with n planks is half the harmonic series up to n, which is 1/2 times 1 plus 1/2 plus 1/3 plus 1/nth. Since the harmonic series diverges, the maximum overhang also grows without bound. With enough planks, you can extend the stack as far as you want past the edge of the table. The stack is balanced precariously by the increasingly small contributions of each additional plank. This has been verified experimentally. Physicists have stacked planks and achieved overhangs that would seem impossible to someone unfamiliar with the harmonic series. The mathematical divergence has a physical manifestation. The impossibly slow growth of the harmonic series translates into an impossibly slow but real extension of the overhanging stack. What the harmonic series paradox reveals is that slow growth is not the same as no growth. Slow enough growth, persisted long enough, becomes arbitrarily large. This sounds obvious when stated abstractly, but the harmonic series makes it feel impossible because the terms are shrinking so fast that the growth is invisible at any finite stage. You could add 1 billion terms of the harmonic series and the sum would be around 20. Not impressive for 1 billion terms, but the sum is heading to infinity, not to 20. After 10 billion terms it will be around 23. After a Google terms it will be around 100. Every time you multiply the number of terms by 10, the sum grows by about 2.3. Slow, 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 but never stopping. Whether you find this reassuring or disturbing probably depends on whether you are the kind of person who finds comfort in the idea that persistent small contributions eventually add up to something large, or the kind of person who finds it unsettling that you cannot tell by looking at the current sum where the series is ultimately going. What in your life is like the harmonic series? Growing so slowly that the total looks insignificant at any moment you check it, but growing nonetheless, towards something you cannot see yet because you have not added enough terms. There is a version of this that applies to the accumulation of small habits, skills, and knowledge over a long period of time, and it has the same structure as the harmonic series. Each individual day of practice contributes an almost unmeasurably small improvement. The improvements are real, but they shrink as you become more skilled. The first day of practice produces noticeable gains. The 1000th day produces gains that are smaller, measured in the same absolute terms. The 1,000,000th day, if you could practice for that long, would produce gains smaller still. And yet the total skill accumulated can grow without bound. In the same way the harmonic series grows. Not because any individual day produces significant improvement, but because the improvements, small as they are always positive and always accumulate. The series of improvements is like the harmonic series, each term smaller than the last, the sum growing more and more slowly, but never stopping. What this implies about skill development is something that most frameworks for thinking about practice do not quite capture. The popular 10,000 hours rule suggests a specific threshold after which expertise is achieved. But if improvement follows something like a harmonic series, there is no threshold where the sum stops growing. You do not achieve expertise and then stop. You keep improving, more and more slowly, indefinitely. Whether that is motivating or exhausting depends on your relationship with slowness. The harmonic series does not reward the expectation of rapid progress. It rewards the willingness to keep adding terms, even when each new term is smaller than the last, and the total sum barely seems to move. And it reminds you that what the sum looks like right now is not a reliable indicator of where it is going. 20 after 1 billion terms. That looks like the end of the story, but the story keeps going, slower and slower, toward a number that is larger than any number you can name. What would change about how you approach long-term projects if you genuinely internalize the idea that slow growth, persisted long enough, is indistinguishable from no growth in the short term and infinite growth in the long term? And what is the equivalent of never stopping adding terms in the context of something you care about? One more thing the harmonic series teaches. The divergence is not obvious from any finite stage. The first 1,000,000 terms sum to about 14. That tells you nothing reliably about whether the sum is heading to 15 or to infinity. Only by understanding the mathematical structure, by proving the divergence, can you know for certain that the sum grows without bound. Empirical observation over finite time does not always reveal long-term behavior. A series that looks like it is converging might not be. A trend that looks like it is leveling off might not be. The harmonic series is a reminder that what you see at any finite stage is not always a reliable guide to what happens in the limit. What might be growing in your life so slowly that it looks like it has stopped? And how would you know the difference? The series does not tell you, and neither does the silence. You have to decide to keep adding terms anyway. The ant on a stretching rope. An ant starts at one end of a rope that is 1 kilometer long. The ant walks toward the other end at 1 centimeter per second. After each second, the rope is stretched to be 1 kilometer longer than it was. The ant is carried along with the rope as it stretches, maintaining its relative position on the rope. So after the first stretch, the ant is slightly further from the start and slightly further from the end, both distances having grown proportionally. Will the ant ever reach the other end? At first this seems obviously no. The ant moves 1 centimeter per second. But each second, the rope grows by a kilometer, which is 100,000 centimeters. The ant gains 1 centimeter of progress, and then the rope stretches so that the end is now effectively 100,000 centimeters further away. The ant is not gaining ground. It seems to be losing it, massively, with every passing second. And yet the ant does reach the other end. Given infinite time, the ant completes the journey. The reason involves the same mathematics as the harmonic series. After each second, the ant covers a fraction of the total rope length. In the first second, before stretching, the rope is 1 kilometer and the ant covers 1 centimeter, which is 1/10,000th of the total length. In the second second, the rope is 2 kilometers long and the ant covers 1 centimeter, which is now 1/20,000th of the total length. Each second, the ant covers a fraction of the rope equal to 1 divided by 10,000 times n, where n is the current second. These fractions accumulate over time. The total fraction covered by the ant is 1 over 10,000 times the sum of 1 plus 1/2 plus 1/3 plus 1/4, which is 1 over 10,000 times the harmonic series. And since the harmonic series diverges, this sum eventually exceeds 1. When it does, the ant has covered more than the whole rope, which means it has reached the far end. The ant reaches the end not in any time a human mind can comfortably hold. The calculation shows that the time required is on the order of e to the power of 10,000 seconds, where e is approximately 2.718. That number so completely dwarfs the current age of the universe that comparing the two is almost meaningless. But mathematically, given unlimited time, the ant gets there. What the ant problem demonstrates is the same lesson as the harmonic series, but in a more viscerally physical form. Progress can look locally like absolute failure and still constitute, globally, eventual success. Each second the ant is losing ground in absolute terms. Each second the far end of the rope is effectively further away than it was. And yet the fractional progress accumulates. The harmonic series ensures that the sum of fractions eventually reaches 1. Mathematicians sometimes call situations like this supertasks, but the ant problem is not really a supertask in the strict sense. A supertask involves completing infinitely many actions in finite time. The ant takes only finitely many steps per second and requires infinite time to finish. The problem is resolved by infinite time rather than compressed into finite time, which is why it has a clean answer where Thomson's lamp does not. Infinite processes over infinite time behave very differently from infinite processes compressed into finite intervals. For human purposes, the ant problem carries something worth sitting with about persistence under conditions that locally seem hopeless. Each second the ant is further from its goal in absolute terms than when it started. Each second the situation looks worse from any local measurement you could take. And yet the fractional coverage accumulates, logarithmically slowly, toward the 100% required. Whether this is a useful metaphor depends on whether the situation you are in actually has the harmonic structure the ant problem requires. The ant's progress works out because the stretching of the rope and the ant's walking speed stand in a specific mathematical relationship that guarantees the fractions sum to infinity. Not every difficult situation has that structure. Some situations genuinely converge to a state where progress becomes impossible, where each effort is not just locally negligible, but globally negligible, where the series of fractional gains converges rather than diverges. The ant on the stretching rope is comforting precisely because it shows that a certain kind of situation, one that looks hopeless locally but has the right global structure, resolves in the ant's favor given enough time. But the comfort only applies if you are actually in that kind of situation. Part of the work of thinking carefully about your own circumstances is figuring out whether your particular rope is stretching in a way that the harmonic series describes, or in a way that converges and eventually leaves you genuinely unable to make progress. Most people do not make this distinction carefully. They either draw the optimistic lesson from the ant problem that persistence always wins, or they dismiss it entirely as a mathematical curiosity with no practical meaning. Both responses miss what the problem is actually saying. Persistence wins when the structure of the problem has the right mathematical form. Whether your problem has that form is a separate question, and one that the ant problem cannot answer for you. There is one more feature of the ant problem that is easy to overlook. The rope is stretching uniformly, which means every part of the rope, including the part behind the ant, is getting longer. When the rope stretches, the ant does not stay where it was in absolute terms. It is carried forward proportionally. A tiny but real contribution to the ant's progress comes from the stretching itself, from the fact that the rope is expanding uniformly beneath it. This is unusual. Most metaphors for progress assume a static environment in which the goal stays fixed and you move toward it. The ant problem describes a dynamic environment in which the environment itself is expanding, carrying you forward slightly while simultaneously moving your destination further away. The net effect is negative in absolute terms at every step, but the carrying forward effect, tiny as it is, contributes to the fractional progress that eventually adds up. Whether there is anything in ordinary human experience that resembles the stretching of the rope is not obvious, perhaps a field that is itself growing, so that being in it carries you forward even when your individual effort seems negligible, perhaps a community or a tradition that expands and in expanding creates more of the thing you are trying to reach, even as the total space of what could be reached also grows. Perhaps the experience of being embedded in a culture that is genuinely developing so that the very ground you are standing on moves you incrementally in a useful direction, even when your own steps are tiny. Or perhaps the analogy breaks down there and the rope is just a rope. What the ant problem leaves you with, finally, is a question about timescales. The ant gets there, but the time required is so enormous that no practical being could ever observe the completion. From inside the problem, the ant experiences nothing but constant relative loss, nothing but the end getting further away in absolute terms, nothing but the accumulating gap between where it is and where it needs to be. The completion exists mathematically, but it exists at a timescale so remote that it functions, practically, as never. Whether a success that arrives after a time incomprehensibly longer than the age of the universe counts as success in any meaningful sense is a question the mathematics does not answer. The ant gets there. You would not be there to see it. What would it change about how you think about a long and apparently failing effort if you knew it was guaranteed to succeed, but only after a time longer than you could possibly live to see? And is that kind of guarantee worth anything at all? There is a version of the ant problem that applies to learning a difficult subject. When you start learning any deep field, the total amount that exists is already far beyond what you could cover in a lifetime. New results and new questions emerge faster than you can move through what already exists. At every moment you know a smaller fraction of the total than when you started, even as your absolute knowledge grows. And yet people reach genuine mastery of portions of fields, not by covering more ground in absolute terms, but by covering enough of the relevant portion. The ant does not need to cover the whole rope, it only needs to reach the far end, which stays at a fixed relative position even as the rope expands around it. The ant does not know the gap is closing. From its perspective, the end is always further than it was, progress always smaller than the setback. And yet it keeps walking. The mathematics says that is enough. Bertrand's paradox. Pick a random chord of a circle. What is the probability that the chord is longer than the side of an equilateral triangle inscribed in the same circle? Joseph Bertrand posed this question in 1889, and it has been quietly unsettling probability theorists ever since. Not because the question is hard to answer, but because it has 3 different correct answers depending on how you interpret the phrase "pick a random chord." All 3 derivations are mathematically valid. All 3 give different numbers. Start with the first method. Fix one endpoint of the chord anywhere on the circle, then pick the other endpoint randomly from the remaining arc. Because of the circle's symmetry, you can assume the fixed endpoint sits at the top. The inscribed equilateral triangle, with one vertex at the top, divides the remaining arc into sections. A chord is longer than the triangle's side when the second endpoint falls in the arc between the other 2 vertices of the triangle, which is exactly 1/3 of the full circle. So the probability is 1/3. Now try the second method. Pick a random radius of the circle, then pick a random point along that radius, then draw the chord perpendicular to the radius through that point. A chord drawn this way is longer than the triangle's side when the chosen point is closer to the center than the midpoint of the radius, because the triangle's sides touch the circle at exactly the midpoint of each radius. So the midpoint divides the radius in half, and the chord is longer when the point falls in the inner half. Probability 1/2. Try the third method. Pick a random point anywhere inside the circle and draw the unique chord for which that point is the midpoint. A chord is longer than the triangle's side when its midpoint falls inside a smaller circle of half the radius, inscribed inside the original. The area of the inner circle is 1/4 of the area of the outer circle, so the probability is 1/4, 1/3, 1/2, 1/4. All three answers come from asking the same question about the same geometric setup. All three are correct, given the method used to generate the random chord. Bertrand's paradox is not that the mathematics is wrong, it is that the question was never fully specified. When you say pick a random chord, you have not actually said what you mean by random. Different interpretations correspond to different probability distributions over chords, and those distributions produce different answers. This might seem like a technicality. Just choose one interpretation and move on. But the paradox cuts deeper than that. When you say pick a random point, pick a random time, pick a random object from some collection, you are implicitly assuming that random has a well-defined meaning in that context. Bertrand's paradox shows that it often does not. Randomness is not a property of a collection of things. It is a property of the process by which you select from that collection. Change the process and you change the probability. Mathematicians have tried to resolve the paradox by finding a natural or canonical way to distribute randomness over chords. One approach, associated with the maximum entropy principle, says you should choose the distribution that makes the fewest assumptions. But even this approach produces a specific answer, 1/2, by privileging a particular symmetry, and there are other symmetries you could privilege that would give different answers. No uniquely correct choice emerges from pure mathematics alone. What Bertrand's paradox ultimately reveals is that probability theory requires specifying a sample space and a probability measure on that space before any probability question is well defined. When you skip this step, when you talk about something happening randomly without specifying what random means here, you leave the question open in a way that might not be obvious until someone calculates 3 different correct answers from the same setup. Every time you make a claim about what would happen randomly, about base rates, or how likely something is to occur by chance, you are implicitly assuming a specific probability distribution. Sometimes that assumption is natural and uncontroversial, and nobody needs to make it explicit. But sometimes it is deeply contested, and the contestation is exactly what Bertrand's paradox is pointing at. Scientific papers sometimes report results as unlikely to be due to chance, with p-values below some threshold. Those papers are implicitly assuming a specific null distribution, a specific probability distribution over what would happen by chance. If someone else has a different null distribution, they might reach a different conclusion from exactly the same data. This is not always wrong or dishonest. It is sometimes an unexamined assumption masquerading as a fact about probability. Bertrand's paradox is a clean, geometric version of something that happens constantly in applied statistics and everyday reasoning about likelihood. The question sounds well posed. The calculation looks straightforward. And there are multiple correct answers because the question was never as fully specified as it seemed. Poincaré used the paradox to argue that probability in geometric settings required careful new foundations. His work contributed to measure theory, giving mathematicians tools to specify precisely what random means in any context. Within mathematics, the paradox dissolves the moment you fix a measure. Outside mathematics, the unresolved version keeps reappearing wherever people argue about what would happen by chance without specifying their distribution. The formal resolution demands a precision that the real world rarely provides. If someone told you that an event was unlikely to happen by chance, what would you need to know to evaluate that claim honestly? And how often do you actually have that information when you encounter it in the world? There is a deeper issue that Bertrand's paradox raises, one that goes beyond statistics and into the foundations of probability theory itself. Since the 1920s, the dominant approach to probability in mathematics has been the axiomatic framework developed by Andrei Kolmogorov. On this approach, probability is defined by a set of axioms, a sample space, and a measure on that space. The axioms tell you how probabilities must behave. The sample space and measure tell you what the probabilities are in any specific situation. On this view, the Bertrand paradox is resolved trivially. There is no paradox because there is no such thing as the probability of a random chord being longer than the triangle side until you specify a probability measure on the space of chords. 3 different measures give 3 different answers. Choose one and the problem is solved. The question of which measure to choose is not a mathematical question, but a practical one that depends on what physical process you are using to generate the chords. But this resolution, satisfying as it is within mathematics, leaves something philosophically uncomfortable. In practice, people talk about probability without specifying measures constantly. What is the probability that life exists elsewhere in the universe? What is the probability that a particular business strategy will succeed? What is the probability that the person you are thinking about right now is also thinking about you? None of these questions come with an explicit probability measure attached, and yet people reason about them, make decisions based on them, and sometimes reach completely opposite conclusions from the same information. Bertrand's paradox is a reminder that those conversations are often less well defined than they appear, not because the reasoning is sloppy or the participants are unintelligent, but because the question genuinely has not been fully posed. Different people are implicitly answering different versions of the question while assuming they are answering the same one. Recognizing this adds a step to how you engage with probability claims. Before you calculate the probability, make explicit what you mean by random in this context. What is your sample space? What is your measure? These questions are not always easy to answer, but asking them is more honest than skipping them and producing a precise-looking number that conceals an unexamined assumption beneath a layer of mathematical confidence. 3 answers, 1 question, all of them correct given their own assumptions. The assumptions, when left unstated, are entirely invisible, and the invisibility is precisely what makes them dangerous. What probability have you assigned to something in your own life without asking yourself what distribution you were using? And would the answer change if you finally asked? Most people never do, and it rarely occurs to them to wonder what they missed by not asking. The cord is drawn. The question remains open. Cantor's paradox. Georg Cantor spent the last decades of his life building a consistent theory of infinite sets, and in doing so, he created one of the most productive paradoxes in the history of mathematics. A paradox that bears his name, one that ultimately required a fundamental restructuring of the foundations of the entire discipline to resolve. Cantor had proved that for any set, the collection of all its subsets, called the power set, is strictly larger than the original set. Not just larger in an informal sense, strictly larger in the precise sense that you cannot put the two sets in one-to-one correspondence. No matter how you try to match elements of the original set with subsets, some subsets will always be left unpaired. The power set is always a larger infinity than the set itself. This theorem works for every set you can name. A set with 3 elements has a power set with 8 elements. A set with 10 elements has a power set with over 1,000. An infinite set with countably many elements has a power set with uncountably many elements. Go further and that uncountable infinity has a power set larger still, and so on forever upward, an infinite hierarchy of infinities, each strictly larger than the last. Now ask a natural question. What about the set of all sets? Suppose you could collect every set that exists into one big container. Call it V, for the universe of all sets. What is the power set of V? By Cantor's theorem, the power set of V must be strictly larger than V. But V is supposed to contain every set that exists. Every subset of V is itself a set, so every subset of V must already be in V. Which means the power set of V, the collection of all subsets of V, cannot be larger than V because all its elements are already members of V. But Cantor's theorem says it must be larger. Contradiction. This is Cantor's paradox. The set of all sets cannot exist because its power set would have to be simultaneously larger than it and contained within it, which is impossible. When Cantor first encountered this, he distinguished between sets and what he called inconsistent multiplicities, collections too large and contradictory to be treated as genuine mathematical objects. But his framework was informal, and he struggled to make the distinction precise. Other mathematicians, including Bertrand Russell, who discovered his own related paradox around the same time, recognized that the naive assumption that any coherent description defines a set was leading mathematics into genuine contradictions. The resolution came in the early 20th century with the development of axiomatic set theory, particularly the Zermelo-Fraenkel axioms. On this approach, not every description defines a set. You can only form sets in certain controlled ways, specified by the axioms. The collection of all sets is not a set. It is a proper class, a collection too large to be a set, and the axioms are specifically designed to prevent it from being treated as one. This is a real and drastic response. Mathematicians had to admit that the intuitive concept of set, as any well-defined collection of objects, was inconsistent. You could not have a set containing all sets. You could not have a set containing all sets that do not contain themselves, which is Russell's version of the same problem. The axioms were designed to rule these out by drawing an explicit boundary between what counts as a set and what does not. What Cantor's paradox exposed is something genuinely unsettling about the nature of mathematical infinity. Every time you reach an infinity, Cantor's theorem shows you there is a strictly larger one. You cannot reach the top. There is no largest infinity. And if you try to imagine all infinities collected together, you get an object so large that it generates a contradiction, so large that it cannot be a set at all. The hierarchy of infinities is not just endless, it is, in a precise sense, too large to be captured by any single mathematical object. You can always go higher, but you can never collect all the heights into one place without breaking the rules that make the heights meaningful. Modern set theory handles this by distinguishing carefully between sets and proper classes, between collections that can be mathematical objects and collections that are simply too large to be collected. But this distinction is not fully satisfying philosophically. Why should some collections get to be sets and others not? The answer the axioms give is essentially because if we allowed them all to be sets, we would have contradictions, which is pragmatically sound but does not fully explain why mathematical reality, if there is such a thing, is structured this way. There is a version of this that operates in the philosophy of knowledge. Consider the collection of all truths. Every statement that is true gathered together, this seems coherent. Truth is well defined, at least in principle. Any given statement is either true or false. So the collection of all true statements should be a perfectly good collection. But Cantor's approach suggests something strange about this. Statements about the collection of all truths are themselves truths, and must therefore be in the collection. Statements about those statements are also truths, in an infinite regress. When you try to treat the collection of all truths as a single unified object, it generates the same kind of self-reference that produces paradox in set theory. The collection might be too large to be a unified object at all, more like a proper class of truths than a set of them. Whether that is a genuine limitation or a feature of how description works is still contested. But the shape of the argument is the same as Cantor's. Go high enough and you run out of room to collect everything without contradiction. The attempt at completeness is what produces the problem. Cantor himself died in 1918 in a sanatorium, still believing in the transfinite, still working on questions his own theorems had raised and that he could not resolve. He believed the paradoxes were pointing at something real he had not yet understood, not at a pragmatic choice of axioms. Whether he was right is a question mathematical practice has not settled, because mathematical practice does not settle questions about what mathematics says. What is the collection of all your beliefs? And if you tried to treat it as a single unified object, a coherent worldview, would it contain beliefs about itself that it could not accommodate without breaking something? There is one more dimension of Cantor's paradox worth sitting with. The axiomatic resolution has a strange quality to it. Mathematicians drew a line and said, collections on this side are sets and can be treated as mathematical objects. Collections on the other side are proper classes and cannot. The line is drawn precisely where it needs to be to avoid paradox, not because of any prior principle about what sets should be, not because some deeper understanding of mathematical objects revealed a natural boundary. The line is there because putting it there prevents contradiction. This is pragmatically sensible. Modern mathematics is built on this foundation and the foundation holds. Theorems are proved, structures are studied, applications are made. But the justification for the line is essentially circular. We draw it here because the line here prevents contradiction. And we want to prevent contradiction because contradiction breaks everything, which it does. But this means the foundations of mathematics were chosen to work rather than discovered to be correct. Whether that is troubling depends on your philosophy. If you believe mathematics describes a pre-existing reality of abstract objects, the pragmatic choice of axioms seems like it might be missing or distorting something real. If you believe mathematics is a human construction designed for coherence and usefulness, the pragmatic choice seems perfectly appropriate, just engineering for consistency. Cantor, who was a Platonist and believed he was discovering real truths about infinity, would probably have found the pragmatic resolution inadequate. He spent years trying to understand the paradoxes as revelations about the structure of infinity rather than as prompts to change the rules. He never fully succeeded. Whether the rules needed changing, or whether the paradoxes were pointing at a deeper truth he was simply unable to reach, is something that remains genuinely open. What would it mean to be right about infinity and unable to prove it, because the proof would require tools the mathematical community had agreed to prohibit precisely because they generated contradiction? And is there anything in ordinary life that has that same structure, a truth you cannot establish because the only path to it runs through something everyone has agreed to avoid? Nobody knows. The Burali-Forti Paradox, before Cantor's paradox, before Russell's paradox, there was a quieter contradiction that appeared in 1897 when an Italian mathematician named Cesare Burali-Forti published a paper on ordinal numbers and noticed something deeply wrong at the edge of what his framework could describe. What he found was not a mistake in a proof, it was a crack in the foundations of a branch of mathematics that had barely been constructed. Ordinal numbers are one of Cantor's inventions. You already know the natural numbers, the counting numbers that go 1, 2, 3, 4 and so on. Ordinal numbers extend this into the infinite. After all the natural numbers comes a first infinite ordinal, which Cantor called omega. After omega comes omega plus 1. After that, omega plus 2. You can keep going, adding to omega, multiplying omega by itself, raising omega to the power of omega, and each operation produces a new ordinal number larger than anything that came before it. Ordinals are used to describe the order type of well-ordered sets, sets where every non-empty subset has a least element. Every well-ordered set has an ordinal that captures its structure. The ordinal tells you how the elements are arranged in relation to each other, not how many there are, but in what order. Two well-ordered sets with the same ordinal can be matched up in a way that preserves their order. Burali-Forti noticed the following. Since ordinals describe order types of well-ordered sets, and since the ordinals themselves can be arranged in order from smallest to largest, the collection of all ordinals is itself a well-ordered set. And a well-ordered set has an ordinal, so the collection of all ordinals has an ordinal, call it omega. But here is the problem. Omega is an ordinal. So omega must be in the collection of all ordinals. But omega was supposed to be the ordinal of the collection of all ordinals, which means omega must be larger than every ordinal in the collection. Omega must be larger than every ordinal, including itself. An ordinal cannot be larger than itself. Contradiction. The collection of all ordinals cannot exist for the same reason the set of all sets cannot exist. Any attempt to collect all ordinals into a single object generates a contradiction, because the collection would need an ordinal of its own, and that ordinal would have to be both inside and outside the collection simultaneously. Burali-Forti published this result before Russell published his paradox, and before Cantor's paradox was widely known. At the time, the mathematical community was not immediately sure what to make of it. Some thought it revealed a flaw in Cantor's theory of ordinals. Some thought it was a genuine paradox requiring a response at the level of foundations. Others thought it was simply the observation that there is no largest ordinal, which is true but does not fully capture the problem. The resolution, like the resolutions to Cantor's and Russell's paradoxes, came through axiomatic set theory. In Zermelo-Fraenkel's set theory, the collection of all ordinals is not a set, it is a proper class. You can refer to it informally, you can reason about ordinals in general, but you cannot treat the collection of all ordinals as a single mathematical object of the same kind as the sets it contains. The axioms are specifically designed to prevent this, and they succeed in preventing the paradox by preventing the question from being fully posed. What Burali-Forti's paradox revealed, and what Cantor's and Russell's paradoxes confirmed in their different ways, is that the naive idea of set, as any coherent collection of objects you can describe, is inconsistent. You can describe collections that cannot exist as sets without breaking mathematics. The ordinals are one of them. All sets are another. Sets that do not contain themselves are another. There is something interesting about the specific structure of Burali-Forti's result compared to the other paradoxes of naive set theory. Russell's paradox works through self-reference at the level of membership, whether a set contains itself. Cantor's paradox works through the power set operation and size. Burali-Forti's paradox works through ordering, through the fact that ordinals are themselves ordered, and the ordering generates a new ordinal not already in the collection. What this suggests is that the paradoxes of naive set theory are not all the same paradox wearing different costumes. They arise from different properties of collections, from membership, from size, from order, and each reveals a different way that trying to collect everything generates a contradiction. The axioms of set theory are essentially a list of prohibitions, each one corresponding to a paradox that showed what cannot be allowed. Whether the list is complete is a live question. The history of set theory suggests that mathematical foundations contain surprises that were not anticipated when the foundations were built. New axioms have been proposed and debated since Zermelo and Frankel's original work. Whether any of them patch holes that current mathematics has not yet stumbled into is something no one can say with confidence. Burali-Forti published in 1897. Cantor responded by saying he had made an error, that the collection of all ordinals was not a consistent set, but Cantor's response was vague, and mathematicians who looked carefully were not fully convinced. Russell, discovering his own paradox a few years later, described it as a shock. Frege, to whom Russell wrote a letter just as Frege was completing his foundational work, responded with something close to resignation. He wrote that a scientist can hardly meet with anything more undesirable than to have the foundations of his work collapse just as it is finished. Burali-Forti found the crack first. The repair is still ongoing. There is a version of the ordinal hierarchy that appears in human experience without the mathematical precision. When you try to understand a complex system, you develop a model of it. A good enough model lets you make predictions and identify patterns, but the model itself is now something to understand, and you can form a model of your model. And a model of that? Each level of understanding generates a new object that could itself be understood, and the process never reaches a final level where nothing new remains. Whether this infinite regress of models is a limitation or just what understanding is depends on what you think understanding is for. If the goal is a complete description that leaves nothing out, the regress is a problem. If the goal is a description good enough for current purposes, the regress does not matter. You stop whenever you have what you need. What is the most complete understanding you have of something you care about? And what would it take to be confident that no higher level understanding of your understanding was missing something important? Burali-Forti could not answer that for ordinals, and the question remains exactly as open now as it was in 1897, as it always was. Skolem's paradox. Thorolf Skolem was a Norwegian mathematician who, in 1922, pointed at something strange inside the foundations of set theory that most mathematicians would have preferred not to think about too carefully. What he found was not a contradiction exactly. It was something more unsettling, a true statement that seemed to be impossible. Set theory, as formalized by Zermelo and Frankel, contains axioms that guarantee the existence of uncountable sets. The axiom of power set, combined with Cantor's theorem, produces sets that cannot be put in one-to-one correspondence with the natural numbers. Uncountable sets genuinely exist within the theory. Cantor's diagonal argument proves they cannot be listed. This is a theorem, provable from the axioms, as solid as any result in mathematics, and yet, by a theorem in mathematical logic called the Löwenheim-Skolem theorem, any set of axioms that can be satisfied at all can be satisfied by a model that is countable. Meaning, you can find an interpretation of the axioms, a universe of mathematical objects satisfying all the rules, in which there are only countably many objects total. Now put these together. Zermelo-Frankel's set theory has models. By the Löwenheim-Skolem theorem, it has countable models, models containing only countably many sets. But one of the theorems provable in Zermelo-Frankel is that uncountable sets exist, which means the countable model must contain a set that, according to the axioms, is uncountable. How can a set be uncountable if the model it lives in contains only countably many things? This is Skolem's paradox, and it is genuinely strange. The short answer is that uncountability is relative to a model. A set is uncountable within a model if there is no function in that model that maps the natural numbers onto the set. In the countable model, the set that the axioms declare to be uncountable is indeed uncountable within the model, because the function that would map naturals to its elements does not exist as an object within that model. From outside the model, looking in, you can see that such a function exists, that the set is actually countable. But inside the model, the function is absent, and the set appears uncountable. Skolem himself found this deeply troubling. He used it to argue against the idea that set theory could serve as a foundation for mathematics, precisely because the key concepts of set theory, including cardinality and uncountability, turned out to be relative to a model rather than absolute. The same set can be countable in one model of set theory and uncountable in another. Which model captures what these words really mean? Most mathematicians responded to Skolem's concerns with something between dismissal and acceptance. The dismissal position says there is no paradox here, just a mathematical fact that requires getting used to. Uncountability is indeed relative to a model, and that is simply what uncountability that the formal notion fails to capture. The acceptance position says Skolem was right to be troubled, that formal set theory is a less secure foundation than its proponents believed, and that the relativity of cardinality to models reveals something genuinely disturbing about the relationship between mathematical language and mathematical reality. What the paradox points at is the gap between what a formal system says and what the words in the formal system mean. When Zermelo-Fraenkel's set theory proves that uncountable sets exist, is it proving something about sets that genuinely exist in some mind-independent mathematical reality? Or is it proving something about how the words uncountable and set behave inside a formal game, a game that can be played in countable models as easily as uncountable ones? If the second, then the question of whether uncountable sets really exist, in any robust sense, is not settled by the theorem. The theorem proves that within the formal system, certain things are true. Whether those truths correspond to anything outside the formal system is a different question, one that formal mathematics is not designed to answer. This connects to a broader question about the relationship between mathematical proof and mathematical truth. A proof shows that if the axioms are true, then the conclusion is true. But whether the axioms are true, whether they describe something real, rather than just something consistent, is not itself a mathematical question. Skolem's paradox makes this explicit by showing that the same axioms can be realized in radically different ways, in a countable universe or an uncountable one, and the axioms themselves cannot distinguish between these realizations. Whether uncountability is a real feature of mathematical reality or a feature of how we talk within a particular formal system is a question that has not been settled and shows no sign of being settled soon. Skolem thought this showed that set theory was the wrong foundation. Most of the mathematical community disagreed and kept building. Both positions are still represented in the philosophy of mathematics today. What does it mean for a statement to be true within a system but false when viewed from outside it? And is there always an outside from which the view is clearer, or does every outside have its own outside, leaving the question of absolute truth permanently out of reach? There is a version of Skolem's insight that operates in human experience without any logic. When you use a concept within a particular context, the concept has a meaning that is shaped by that context. Move the same concept to a different context, and it might mean something entirely different, even if the words are identical. Consider the word fair. Within the context of a competitive game, fair means each player follows the same rules. Within the context of distribution, fair might mean equal shares, or shares proportional to contribution, or shares proportional to need, depending on which framework you are in. The same word, in different frameworks, picks out genuinely different things, and someone reasoning from one framework and someone reasoning from another can look at the same situation and reach opposite conclusions about whether it is fair, not because they are irrational, but because they are inside different models. Skolem's paradox says this framework dependence reaches all the way into formal mathematics, into a domain that was supposed to be the place where concepts finally get pinned down precisely. Uncountability, which sounds maximally precise, turns out to be relative to a model. The same set is uncountable inside one model and countable when viewed from outside. The precision of the formal language did not eliminate the relativity. It just made the relativity more surprising when it was discovered. What does it mean that even our most rigorous tools for describing mathematical reality leave the description underdetermined? And is there any domain, mathematical or otherwise, where the concepts we use to describe things are genuinely free of framework dependence? Or does every description carry its model with it, determining what the words mean in ways that are not always visible from inside? Skolem thought this was a serious problem. Most of the people who came after him thought it was manageable. The question of who was right is still open, and will probably remain open, because the answer depends on what you think description is for. The Löwenheim-Skolem theorem has another implication worth sitting with. It applies not just to set theory, but to any first-order theory with an infinite model. Number theory, analysis, geometry, all of them have countable models if they have any infinite model at all. First-order logic, which is the language of standard mathematical foundations, cannot force a theory to have only large models. No matter how many axioms you write, if the theory talks about infinite things, it can be interpreted in a countable universe. This is not a gap in the specific axioms anyone chose. It is a limit on the expressive power of the logical language itself. First-order logic simply cannot say what it would need to say to rule out small models. The language runs out before it can do that. Some mathematicians move to stronger logical languages that can achieve categoricity, that can pin down a theory to a single model up to isomorphism. But those languages come with their own limitations and complications. There is no free lunch in the trade between expressive power and tractability. Skolem pointed at a genuine feature of how formal language relates to mathematical content. The pointing was clear. The conclusions to draw from it are still contested. And the question of what it means to describe infinity rigorously, and whether any description fully succeeds, is one that remains genuinely and productively open, as it always has been. Richard's paradox. Jules Richard was a French mathematician who, in 1905, published a short paper describing a paradox so compact and so precise that it has occupied logicians ever since. The paradox concerns the relationship between the real numbers and the descriptions of real numbers, and it uses a diagonal argument similar to Cantor's to generate a contradiction at the heart of how mathematical language works. Here is the setup. Consider all possible descriptions of real numbers written in English. A description is a finite string of English words that unambiguously defines a specific real number. Something like the ratio of a circle's circumference to its diameter, which defines pi, or the positive square root of 2, or the limit of the sequence 1 over n as n grows without bound, which defines 0. Every such description, if it works at all, picks out exactly one real number. Now arrange all these descriptions in some order. Because each description is a finite string of letters and punctuation, and because there are only finitely many such strings of any given length, you can in principle list all finitely long descriptions in an order. List them by length first, then alphabetically within each length. Number them 1, 2, 3, and so on. Each description gets a number, and each number corresponds to a description of a real number. Now construct a new real number using Cantor's diagonal method. Look at the first description, which defines some real number. Look at the first decimal digit of that number, change it. If it is 4, write 5. Otherwise, write 4. Look at the second description and the second decimal digit of the real number it defines. Change it the same way. Continue forever down the diagonal, changing each digit. The new number you have constructed differs from the real number defined by the first description in its first digit, from the real number defined by the second description in its second digit, and from every real number in the list in at least one digit. So the new number is not defined by any description in the list. But wait, you just described it. The procedure you followed is itself a finite description in English of a specific real number. Call it the Richard number. So the Richard number should appear somewhere in the list of descriptions. But you constructed it specifically to differ from every number defined by a description in the list. The Richard number is both definable in English and not definable in English. That is the paradox. Richard himself thought the paradox showed something about the illegitimacy of mixing mathematical and meta-mathematical language, of using English to describe mathematical objects and then treating those descriptions as mathematical objects themselves. The paradox arises precisely because you take descriptions, which are linguistic objects, and treat them as if they can be enumerated like mathematical objects, then apply a mathematical procedure to generate a new one. Bertrand Russell analyzed Richard's paradox and categorized it alongside the liar paradox, the barber paradox, and his own paradox about sets, as belonging to a family of paradoxes that arise from vicious circles, from definitions that refer to collections that include the thing being defined. The Richard number is defined by reference to all definable numbers, of which it is supposed to be one. The circularity is what produces the contradiction. The resolution in formal mathematics is similar to the resolution of the liar paradox through Tarski's hierarchy of languages. You cannot define definability within the same language you are using to define things. Definability is a meta-linguistic concept. Tarski's undefinability theorem, proved in 1933, shows precisely that no sufficiently powerful formal language can define its own truth predicate, and by extension its own notion of definability, without producing contradictions. But this resolution requires a sharp separation between object language, the language in which mathematical statements are made, and meta-language, the language in which you talk about the object language. Natural language, including the English in which Richard framed his paradox, does not respect this separation. English freely mixes statements about numbers with statements about numbers, and this mixing is what generates the paradox. What Richard's paradox reveals is something about the limits of informal mathematical reasoning. When you work informally, using natural language to describe mathematical objects, and then treat those descriptions as objects themselves, you open the door to the kind of self-reference that generates paradox. Formal languages avoid this by imposing strict hierarchies that natural language ignores. Whether the strict hierarchies capture what mathematicians actually mean when they talk about definability and description is a question that formal logic sidesteps rather than answers. The hierarchy prevents the paradox. Whether it does so by correctly analyzing the concept of definability or by replacing it with something more restrictive that happens to be consistent is something the resolution leaves open. What can and cannot be described in a finite number of words? If there are real numbers that no finite description picks out, which there must be since the real numbers are uncountable and descriptions are countable, what are those numbers like? And what does it mean to say that a number exists but cannot be described? There is a version of Richard's paradox that operates in everyday language without any mathematics, and it reveals the same self-referential structure in a more immediate form. Consider the phrase, "all the things that cannot be described" in this sentence. If you try to describe what that phrase picks out, you immediately run into the same problem. The phrase is supposed to pick out things that cannot be described in it, but the phrase itself is a description, so it is picking out things that include anything not describable in that phrase, which is most things, but the phrase is itself a description of those things, so the things describable in the phrase include what is describable in the phrase. Most people, encountering this, feel the pull of something going wrong without being able to pin down exactly where. The mechanism is the same as Richard's mathematical paradox. A description refers to the class of all descriptions, of which it is a member, and generates a loop that has no stable resolution. Richard's paradox is often described as a paradox about language and mathematics, but it is more accurately a paradox about self-reference in any sufficiently expressive system. Any system that can talk about its own expressions, that can form descriptions of descriptions, will generate paradoxes of this form when those self-referential descriptions are treated as first-class objects in the same domain as what they describe. Natural language does this constantly. We talk about sentences, we quote sentences, we refer to our own words in the middle of using them. Most of the time this causes no trouble because the contexts are stable enough that the self-reference does not loop in the problematic way. But when you construct situations specifically designed to exploit the loop, as Richard did, the trouble surfaces. Whether this means natural language is fundamentally inconsistent, in the way that naive set theory was, or whether it means natural language is simply not a formal system and should not be evaluated by the standards of formal consistency, is something philosophers of language disagree about. What would it mean for the language you use to think with to contain structures that, when examined closely enough, generate contradictions? And do you think the language you use does contain such structures, or does it somehow avoid the self-reference that trips up every formal system powerful enough to describe itself? Kurt Gödel, developing his incompleteness theorems in 1931, used a construction closely related to Richard's diagonal argument. He showed that any sufficiently powerful formal system can encode statements about its own provability, and that this encoding generates a statement saying of itself that it is not provable within the system. If the system is consistent, this statement is true but unprovable. If the system proves it, the system is inconsistent. The structure is identical to Richard's construction. A formal system generates a statement about itself that leads to an undecidable conclusion. What appeared to be a linguistic curiosity about descriptions of real numbers was pointing at the same phenomenon Gödel used to prove one of the most important results in the history of mathematics. Richard found the crack in 1905. Gödel showed how deep it went in 1931, and the depth has not changed since. Some cracks are features rather than flaws. Whether this one is depends on what you were hoping the system would do. König's paradox. Julius König was a Hungarian mathematician who in 1905 published a paradox closely related to both Richard's paradox and Berry's paradox, but with a slightly different twist that makes it worth examining separately. Where Richard's paradox focuses on descriptions of real numbers, and Berry's focuses on the smallest number, not nameable in a given number of words, König's paradox focuses on a specific structural feature of the real number line and what it reveals about the limits of definability. König's argument starts from a simple observation: there are only countably many finite sequences of words in any language. Every description, every definition, every name for a mathematical object that can be expressed in finitely many words is one of countably many things. But the real numbers are uncountable. There are more real numbers than there are finite descriptions. So most real numbers cannot be described in any finite number of words. Most real numbers are, in the relevant sense, undefinable. Now consider just the real numbers that can be finitely defined. Since there are only countably many finite descriptions, and each description defines at most one real number, there are only countably many finitely definable real numbers. Line them up in some order, and you have a sequence of all the definable real numbers. König's move is to apply a diagonal argument to this sequence. By Cantor's diagonal method, you can construct a real number that differs from every number in the sequence in at least one digit. This new number is therefore not in the sequence of all finitely definable real numbers. It is not finitely definable. But wait, you just defined it. You said, take the sequence of all finitely definable real numbers in some specific order and apply the diagonal construction. That is a finite description. So the number you just constructed is finitely definable, but it was constructed specifically to not be in the list of finitely definable numbers. Contradiction. The resolution is essentially the same as the resolution to Richard's paradox. The phrase, the sequence of all finitely definable real numbers, is not actually a well-defined object in formal mathematics. You cannot collect all finitely definable real numbers into a sequence without specifying, within a formal system, what counts as a definition. And the collection of all definitions within a formal system is itself a formal object, one whose definition either falls outside the system or generates the same self-referential problems the paradox exploits. Tarski's undefinability theorem handles this cleanly in formal settings. Within a sufficiently powerful formal system, you cannot define the set of all sentences that are true in that system, and by extension, you cannot define the set of all real numbers that are definable in that system, at least not using the resources of the system itself. The self-reference required to do so leads to contradiction. But König's paradox, like Richard's, has a life outside formal mathematics. In natural language, people do talk about all describable things, or all things that can be named, treating these as coherent collections. And the paradox shows that this usage, however natural, contains a self-referential loop that formal mathematics cannot accommodate without contradiction. The paradox also points at something philosophically interesting about the relationship between definability and existence in mathematics. If most real numbers are undefinable, in the sense that no finite description picks them out, what is their mathematical status? Do they exist in the same sense as definable numbers? Are they genuinely there on the real number line, occupying positions, but forever unnamed? Or does definability have some role in mathematical existence that the standard Platonist picture ignores? Most working mathematicians are comfortable with the existence of undefinable real numbers. They appear as consequences of the axioms, particularly the axiom of choice, and they are as real as any other mathematical object in the sense of satisfying the same theorems. Whether their undefinability is a merely practical limitation because the definitions are too long for any human to write, or whether it represents a more fundamental gap between mathematical existence and mathematical description, is a question the paradox raises without settling. What does it mean for something to exist but to be beyond description? Not just beyond current description, not just too complicated for anyone to have gotten around to describing yet, but beyond description in principle, unreachable by any finite string of words in any language. Is that a limitation of description or a feature of existence? And is there any difference between those two possibilities? There is a personal version of König's problem that has nothing to do with real numbers and everything to do with experience and language. Most of what you have experienced in your life cannot be described, not because you are inarticulate or because the experiences were too complex, but because the space of possible experiences is vastly larger than the space of possible descriptions. Every moment of your life is a unique configuration of sensation, thought, emotion, and context that has never been precisely replicated and cannot be fully captured by any finite sequence of words. The description is always an approximation, always a compression, always a projection of a high-dimensional experience into the low-dimensional space of language. This is so obvious when stated plainly that it might seem trivial. Of course, descriptions are not the things they describe. Of course, language is not experience. But König's paradox sharpens the point in a specific way. The gap between experiences and descriptions is not just a matter of compression or imperfection. It is a gap in cardinality, in the most fundamental mathematical sense. There are more possible experiences than possible descriptions, in the same way there are more real numbers than descriptions of real numbers. The surplus is not just large, it is infinite in a specific, uncountable sense. What this means practically is that most of what happens to you will never have words that fully fit it. Not because you have not found the right words yet, or because you are not skilled enough with language, but because the right words do not exist and cannot exist. Language is countable, experience is not. Whether this should make you feel the inadequacy of language more acutely, or whether it should make you feel the richness of experience more vividly, is something the paradox does not determine. What it does is make clear that the gap between the two is not a contingent fact about current vocabulary. It is a structural feature of how description relates to what it describes. König's diagonal number, the real number that escapes every finite description, is in some sense the mathematical object most similar to the experience that escapes every sentence. Both are genuinely there, genuinely real in their respective domains, and both are permanently beyond the reach of any finite string of words. What experience in your life has felt most completely beyond description? Not the most intense or the most meaningful, but the one where words felt most completely inadequate, where the gap between the experience and any possible sentence about it felt largest. And what does it mean that you can point at the existence of that gap, even when you cannot fill it? Standard mathematics, built on Zermelo-Fraenkel set theory with the axiom of choice, guarantees the existence of uncountably many real numbers, most of which are undefinable. These numbers exist by virtue of the axioms and theorems of the system, but they cannot be individually picked out by any description. Mathematics asserts the existence of objects it cannot name. Constructivist mathematicians reject this. On their view, if you cannot define it, you cannot assert it exists. Standard mathematics takes the opposite view, asserting existence freely, on the basis of axioms without requiring that the objects be individually accessible. König's paradox does not resolve this debate. It shows that the debate has mathematical content, not just philosophical. The question of what exists in mathematics, and whether existence requires definability, has consequences for what theorems you can prove. The diagonal number exists, no description reaches it, and yet it sits on the number line at a perfectly specific location, as real in the mathematical sense as pi or the square root of 2 or any number anyone has ever named. Most of the number line is made of things like this: unnamed, unnameable, real. The Dartboard Paradox. Pick up a dart and throw it at a dartboard. Assume you are throwing randomly, that the dart is equally likely to land anywhere on the board, and that it always lands somewhere on the board. Now pick any specific point on the dartboard, any single precise location. What is the probability that the dart lands exactly on that point? 0. The probability is exactly 0. Not nearly 0, not 1 in a trillion. Exactly 0. And yet the dart lands somewhere. And wherever it lands, that landing point had probability 0 of being hit. Something with probability 0 just happened. This is the Dartboard Paradox, and it exposes a genuine tension between the mathematics of continuous probability and ordinary intuitions about what probability means. In finite probability, probability 0 means impossible. If there are 10 equally likely outcomes and you assign probability 1/10 to each, then any event with probability 0 simply cannot happen. The impossibility is total and the logic is clean. But on a continuous dartboard, with infinitely many possible landing points, probability 0 does not mean impossible. It means infinitely unlikely in a specific technical sense, so unlikely that in any finite collection of throws, the event would essentially never happen. and yet the event happens on every single throw, because every point has exactly this probability. The mathematics here is not wrong or confused. Lebesgue measure theory, the framework for measuring sizes of continuous sets, handles this cleanly. The probability of hitting any single point is 0 because a single point has measures 0 length, 0 area. Probability for continuous distributions is measured over regions, not individual points. You can ask for the probability of hitting a region of the dartboard and get a meaningful positive answer. You cannot meaningfully ask for the probability of hitting a single exact point, or rather, you can ask, and the answer is 0. But 0 does not mean impossible in this context. What the paradox reveals is a gap between two intuitions that both feel natural. One says that what happens must have been possible, and possible means non-zero probability. The other says that probability 0 is a meaningful mathematical assignment for individual points in a continuous distribution. Both intuitions are valid in their own domains. They conflict in continuous probability, where the second is correct and the first needs to be revised. The revision required is this: probability 0 does not mean impossible for continuous distributions. It means measure 0, which is a technical condition that rules out finite collections of outcomes but does not rule out individual outcomes in continuous spaces. A more careful way to state this is that almost all outcomes happen with probability 0 in a continuous distribution. Events of measure 0 can happen. They just happen in a specific mathematical sense that requires distinguishing between measure-theoretic impossibility and outright impossibility. This distinction becomes important in quantum mechanics, where probability distributions over continuous spaces are central to the theory. The probability of finding an electron at any specific exact point in space is 0. The electron is nevertheless found at a specific point when measured. The measurement produces a definite outcome from a distribution where every individual outcome had probability 0. Physicists are comfortable with this because they are trained to think in terms of probability densities and regions rather than individual points. For everyone else, the Dartboard Paradox produces a lingering discomfort that the mathematical explanation does not fully dissolve. Something happened. Whatever happened had probability 0. Probability 0 events happen every single time you throw the dart. One of them happens, each one as impossible as the next by the naive criterion. One way to sit with this is to notice that the paradox only feels paradoxical because of the specific way we have set up the problem. We imagined an ideal mathematical dartboard with infinitely many points, each with no area at all. Real dartboards and real darts do not work this way. A dart tip has a physical size. The landing region has a physical area. In physical reality, the probability of landing in any region with non-zero area is non-zero. The paradox lives in the idealization, in the passage from physical space to mathematical continuum. But the idealization is not just a simplification. It is the foundation of probability theory for continuous variables, and continuous variables appear throughout physics, engineering, finance, and statistics. Dismissing the paradox as an artifact of idealization does not make it go away. It just moves the discomfort from the mathematics into the relationship between mathematics and the physical world it describes. Whether that relationship is perfectly seamless, whether the continuous mathematics describes something real about physical space, or whether physical space is actually discrete at the Planck scale and the continuous mathematics is just a useful approximation, is a question that current physics has not settled. Every point on the dartboard has probability 0. Every throw lands at a specific point. Both of these things are true simultaneously, every time the dart is thrown, with no contradiction between them. What does it take for you to be fully comfortable with that? And is the comfort earned by understanding or just by familiarity? Every specific sequence of events that produced your life had probability effectively 0, not because any individual event was unlikely, but because the conjunction of all of them, in precisely the order they occurred, was one point from a space so vast that any specific path through it has measure 0. The specific sperm and egg, the specific meeting of your parents, every conversation that shaped you, every book, every person, every term, all of it narrowing down to the specific point that is you, right now, and yet here you are. A probability 0 event happened. The Dartboard Paradox says something precise about this. Every point on the board is equally improbable, and one is always hit. Your specific life is not more improbable than any other specific life. All lives are equally improbable at the level of exact specification. Improbability is simply the universal condition of anything specific existing at all. Asking why this specific thing happened rather than something else is a question that probability assigns the same answer to as every other question of this kind. 0. Nothing that happens was more likely than anything else at the level of exact specification. What does it feel like to be a probability 0 event? And does knowing that every other possible outcome was equally improbable change anything about how that feels? In discrete probability, every outcome has a positive probability, and the probabilities sum to 1. In continuous probability, individual outcomes have probability 0, and the total is still 1, but it is distributed across regions rather than individual points. A single point is too small to hold any positive probability. This means continuous and discrete probability describe genuinely different kinds of things. In continuous distributions, probability density functions assign densities to individual outcomes, and density only converts to probability when integrated over a region. A density can be any positive number. A probability must be between 0 and 1. The two are not the same thing. Most people who learn continuous probability absorb the mechanics without confronting this. You can use the tools without noticing the conceptual break. The Dartboard Paradox makes the break visible by producing a case where the discrete intuition, impossible means probability 0, simply fails in the continuous setting. The dart lands. The landing point had probability 0. This happens every single throw, for every possible landing point, without exception and without contradiction. If that still feels strange to you, you are paying attention. The mathematics is correct. The strangeness is also correct. Both are true at once, and making peace with that requires revising something you probably did not know you believed about what probability 0 means. How can infinitely many zeros sum to 1? They cannot in the ordinary sense. Integration accumulates density rather than discrete chunks. The sum of infinitely many zeros is not 1. The integral of a probability density over the whole board is 1. Different operations, same numerical answer, different mathematical mechanisms. What the Dartboard Paradox reveals is that intuition, built from counting, does not transfer cleanly to continuous measurement. Counting and measuring are different operations at their foundations. Infinity makes the difference visible in ways that finite experience never does. The cardinality of the continuum. Pick any 2 points on a line segment. Between them is another point. Between any 2 points is always another. No matter how close together 2 points are, you can always find a third point between them. The real number line is dense in this sense, packed so tightly that there are no gaps, no smallest distances, no adjacent points at all. How many points are on a line segment? Infinitely many, obviously. But what kind of infinity? Countable, like the natural numbers, or uncountable, like the full real line? Cantor proved it is uncountable. There are more points on any line segment, however short, than there are natural numbers. The line segment contains a strictly larger infinity than the counting numbers. But here is where things get strange in a different direction. How many points are on a line segment 1 centimeter long compared to a line segment 1 kilometer long? Intuitively, the kilometer-long segment should have more points. It is 1,000 times longer. It contains, in some sense, 1,000 times as many positions. But it does not. Both segments contain the same number of points, in the precise sense that you can put their points in one-to-one correspondence with nothing left over. Take any point on the short segment, scale its position by a factor of 1,000, and you get a point on the long segment. Every point on the short segment maps to exactly 1 point on the long segment, and every point on the long segment maps back to exactly 1 point on the short segment. The cardinality is the same. Go further. How many points are on a line segment compared to a full infinite line? The infinite line should surely have more points. It extends forever in both directions, while the segment has endpoints. But again, the cardinality is the same. You can map any point on the full line to a point on the segment using an appropriate function, such as the arctangent, which compresses the entire real line into the interval from -π/2 to +π/2. Even further, how many points are on a line compared to a plane? A plane is two-dimensional. A line is one-dimensional. The plane seems vastly larger. It should contain far more points. But the cardinality is the same. Cantor proved this in 1877 and was so surprised he wrote to his colleague Dedekind that he saw it but did not believe it. The proof involves a clever interleaving of decimal digits. Given a point in the plane with coordinates x and y, you can interleave the decimal digits of x and y to produce a single real number that encodes both coordinates. The mapping is 1-to-1 and onto, establishing equal cardinality. A line and a plane have the same number of points, and by the same argument, so does 3-dimensional space, and 4-dimensional space, and any finite dimensional space at all. All of them contain the same cardinality of points, called the cardinality of the continuum, and denoted C. This result so disturbed mathematicians at the end of the 19th century because it seemed to destroy the concept of dimension as a measure of size. If a line and a plane have the same number of points, in what sense is the plane bigger? The answer, worked out by Cantor himself and later made rigorous by others, is that dimension is not about how many points a space contains, it is about the structure of the space, specifically about the properties of the continuous maps between it and other spaces. Two spaces can have the same number of points and completely different dimensions, because dimension is a topological property, not a cardinality property. A line and a plane have the same cardinality, but different topological structures. The difference between a line and a plane is not how many points they contain, but how those points fit together, how neighborhood relationships work, what kinds of continuous deformations are possible. This separation of cardinality from topology was one of the conceptual breakthroughs of the late 19th and early 20th century. Before Cantor, mathematicians might have assumed that bigger spaces, in the intuitive geometric sense, would also be bigger in the set theoretic sense. Cantor showed the two notions of bigger were completely independent. Geometric size and set theoretic sense are different kinds of measurement, and neither determines the other. What this reveals about infinity is something that runs through all the paradoxes in this series. Our intuitions about size, comparison, and measurement were built from experience with finite things arranged in space. When you move to the infinite, those intuitions fail not in one way, but in many different ways, each one revealing a different aspect of how the finite concepts do not generalize. Countability and uncountability come apart from what you might expect. Dimension and cardinality come apart. Measurability and existence come apart. Every time a finite intuition is pushed into the infinite domain, it fractures along some line that was invisible while you were dealing with finite things. The cardinality of the continuum sits near the center of a question that Cantor could not answer, and that turned out to require entirely new tools to address. Is there any infinity between the countable infinity of the natural numbers and the uncountable infinity of the real numbers? Cantor believed not, and called this the continuum hypothesis. He worked on it for decades, and could not prove it. In 1940, Kurt Gödel showed that the continuum hypothesis is consistent with the standard axioms of set theory, meaning you can assume it is true without contradiction. In 1963, Paul Cohen showed that its negation is also consistent, meaning you can assume it is false without contradiction either. The continuum hypothesis is independent of the axioms. Set theory cannot determine whether there is an infinity between the naturals and the reals. Both possibilities are equally compatible with everything else we know. The question Cantor spent the better part of his adult life trying to resolve turned out to be unanswerable not because it was too hard, but because the axioms themselves do not have enough information to settle it. How many points are on a line? More than you can count, fewer than you might imagine if you thought dimension determined size. And the question of exactly where on the infinite hierarchy of infinities the answer sits is one that mathematics has declared, with proof, to be beyond what mathematics can currently answer. What does it mean for a question to be unanswerable not because we lack information, but because the rules of the system we are using to answer questions do not settle it one way or the other? And is that kind of unanswerability a feature of the question or a feature of the system, or both? Cantor spent decades on the continuum hypothesis and could not resolve it. He came to believe there was no intermediate infinity between the naturals and the reals. He was not wrong in the sense of being inconsistent. The belief was compatible with the axioms. He just could not prove it. Gödel confirmed the belief was consistent in 1940. Cohen showed the opposite was also consistent in 1963. Both beliefs were always compatible with everything else in set theory. The axioms simply did not have enough information to choose between them. Whether a question is genuinely open or just currently unresolved feels different from inside the question. Cantor felt like he was missing a proof. He did not know he was working in a domain where the proof was not available from any starting point, because the starting point itself did not settle the question. Most of what you believe about yourself and the world has the same character, compatible with what you know, not provable from what you know, good enough to act on, or not, depending on what you need from it. If the axioms of set theory cannot settle whether there is an infinity between the naturals and the reals, those axioms are genuinely incomplete. Not incomplete by having mistakes, but incomplete in the sense that true mathematical statements exist that the axioms cannot reach. Gödel believed the continuum hypothesis was false, and that better axioms would settle it. Cohen was less sure there was a fact of the matter. He leaned toward the view that multiple incompatible set theories could each be consistent, and that choosing between them was not about truth but about usefulness. Both positions are still held today. Whether mathematical truth is fixed and waiting to be found, or whether it is shaped by the axioms we choose, is a question the independent result makes concrete rather than abstract. What does it mean for something to be true but unprovable from where you are standing? And is that a property of the question or of the system you are using to approach it? The Vitali Set Paradox. Giuseppe Vitali was an Italian mathematician who in 1905 constructed something that should not exist. He built a set of real numbers that has no length, not in the sense that its length is zero, but in the stronger and stranger sense that no coherent notion of length can be assigned to it at all. His construction did not violate any theorem. It was entirely valid given the axioms he was working with, but it revealed that the intuitive concept of length, the idea that every set of real numbers has a size that can be measured, was simply wrong. Before Vitali, mathematicians hoped that the real number line could be divided into pieces each of which had a well-defined length, and that the total length of the line could be recovered by adding up the lengths of the pieces. Henri Lebesgue had recently developed a precise theory of measure that made this hope rigorous for many sets, but Vitali showed that the hope could not be fully realized. Some sets of real numbers are non-measurable. They do not have a length, and no consistent extension of the notion of length can assign them one. Here is how the construction works. Two real numbers are equivalent if their difference is rational, meaning if you subtract one from the other, you get a fraction or an integer. This divides the real numbers between 0 and 1 into equivalence classes, where each class contains all numbers that differ from each other by a rational amount. Every real number in the interval belongs to exactly one class, and there are uncountably many classes. Now use the axiom of choice to select exactly one representative from each equivalence class. The resulting collection is called a Vitali set. By construction, it contains exactly one number from each equivalence class, and since there are uncountably many classes, the Vitali set contains uncountably many numbers. Now suppose for contradiction that the Vitali set has a well-defined length, some number L. Consider all rational numbers between -1 and 1. For each such rational q, shift the Vitali set by q, adding q to every element and taking the result modulo 1 to keep everything in the interval. This gives countably many shifted copies of the Vitali set, one for each rational in that range. These shifted copies are all disjoint from each other. No two of them share a point, and together they cover the entire interval from 0 to 1, because every point in the interval differs from the representative of its equivalence class by some rational amount, and that rational amount is one of the shifts. So the interval from 0 to 1 is covered by countably many disjoint copies of the Vitali set, each with the same length L. If L is 0, the countably many copies have total length 0, but they cover an interval of length 1. Contradiction. If L is greater than 0, the countably many copies have total length equal to infinity, but they fit inside an interval of length 1. Contradiction. Either way, the assumption that L exists leads to a contradiction. The Vitali set has no length. More precisely, it is non-measurable. No consistent assignment of a real number to it as its measure is possible. What the Vitali set revealed is that the intuitive idea of a set of points having a size, however natural it feels, cannot be extended consistently to all possible sets of real numbers. Most sets are fine. Most sets of real numbers you can write down have well-defined measures. But the full collection of subsets of the real line is too wild, too various, too unconstrained to be uniformly tamed by any notion of size. The response from mathematics was not to reject the Vitali set, but to restrict what counts as measurable. Lebesgue's theory of measure assigns sizes to a large and well-behaved collection of subsets of the real line, but explicitly excludes non-measurable sets like Vitali's. The axioms of measure theory are designed so that countable additivity, The property that the measure of a countable union of disjoint sets is the sum of their measures holds for all measurable sets, while non-measurable sets are simply outside the domain where measure is defined. This is a pragmatic response, and it works well for analysis and probability theory, but it means that the real number line contains subsets that genuinely resist measurement, that cannot be assigned a consistent size without contradiction, and that their existence depends on the axiom of choice, which is what allows you to select representatives from uncountably many equivalence classes simultaneously. Whether the axiom of choice is the right axiom to include in mathematics is a question that generates ongoing discussion. Some mathematicians argue that it should be replaced with a weaker axiom that prevents the construction of non-measurable sets. Others argue that accepting non-measurable sets is a price worth paying for the convenience and power the axiom of choice provides elsewhere. The Vitali set sits at the intersection of two things that feel like they should be compatible. Having a set of points, and those points having a length, Vitali showed that in the world of infinite sets, these two things are not always compatible. Points can exist without their collection having a size, and that is a stranger feature of infinity than almost anything else infinity does. What would it mean for something to be real, to be genuinely there, and yet to have no measurable extent? And is the Vitali set a mathematical curiosity, or a glimpse of something that ordinary intuitions about size and space cannot accommodate? The axiom says that given any collection of non-empty sets, we'll have a method to include that axiom in mathematics, is a genuine debate. The axiom says that given any collection of non-empty sets, you can simultaneously select one element from each, even with uncountably many sets and no rules specifying which element to choose. In finite cases, this is obvious. In the uncountably infinite case, it becomes a non-trivial assumption. Many counterintuitive mathematical results depend on it. The Vitali set is one. The Burali-Forti Paradox, which says a solid ball can be decomposed and reassembled into two identical copies, is another. Both use the axiom of choice to produce objects with no physical analog. You cannot actually build a Vitali set or perform a Burali-Forti decomposition in the physical world, not because of engineering limits, but because the pieces involved are non-measurable sets that have no physical realization. Constructivist mathematicians reject the axiom of choice for exactly this reason. Standard mathematics accepts it because the results it enables are consistent and useful. The Vitali set sits at the center of this debate, an object that provably exists but cannot be explicitly described, that is genuinely there but impossible to show. Most people carry the intuition that any collection of things has a size. A bag of marbles can be counted, a region of space can be measured. Size feels like something every collection has. Vitali showed that this fails for mathematical sets. Not because they are too complicated to measure, but because no consistent notion of measurement exists for them. The failure is structural, not practical. The strangeness is invisible from outside. A Vitali set looks like a perfectly ordinary collection of points. You only discover it is not fine by trying to measure it. What would it mean for something to be genuinely real and yet to have no size? And is the Vitali set pointing at a feature of mathematical reality, or at a feature of what happens when axioms permit more than intuition can accommodate? There is one more dimension worth sitting with. The Vitali set is not the only non-measurable set. Once you accept the axiom of choice, non-measurable sets appear everywhere in the structure of the real line. There are in fact more non-measurable sets than measurable ones, in a precise cardinality sense. Most subsets of the real line, in this sense, have no length. We do not usually encounter them because we do not usually work with arbitrary subsets of the real line. The sets that come up in analysis, in probability, in physics, are almost always measurable. The non-measurable ones are exactly the ones that cannot be explicitly constructed, the ones that require choice to exist. So they hide in the background, guaranteed to be there by the axioms, impossible to point at. Whether that makes them real in a meaningful sense is the same question that runs through all of this. The axioms say they are there, the axioms are consistent, and the sets that they guarantee the existence of include things that cannot be measured, cannot be shown, and cannot be described. What is the right relationship to have with the existence of things you cannot see, describe, or measure? And does it change if the existence is mathematically provable rather than just suspected? Probably not, but it is a different kind of not knowing. The Riemann rearrangement paradox. Take the series 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 continuing indefinitely with alternating signs. This is the alternating harmonic series, and it converges. It does not oscillate wildly or grow without bound. The partial sums settle toward a specific value, which turns out to be the natural logarithm of 2, approximately 0.693. You can prove this rigorously, and it is as solid a mathematical result as any other. Now rearrange the terms. Take 2 positive terms, then 1 negative term, and so on. 1 plus 1/3, minus 1/2, plus 1/5, plus 1/7, minus 1/4, plus 1/9, plus 1/11, minus 1/6. This is the same set of terms, just in a different order. The same fractions, the same denominators, the same signs, just arranged differently. This rearranged series does not converge to the natural logarithm of 2. It converges to approximately 1.039, which is the natural logarithm of 2 multiplied by 3/2. The sum changed simply because you changed the order of the terms. Now rearrange again. Take 1 positive term, then 2 negative terms, then 1 positive, then 2 negative. This rearrangement converges to a third value, the natural logarithm of 2 divided by 2, approximately 0.347. Rearrange differently each time and you get a different sum, and Bernhard Riemann proved, in a theorem published posthumously in 1866, that you can rearrange the alternating harmonic series to converge to any real number you like. Any real number. Positive, negative, 0, arbitrarily large, arbitrarily small. Choose a target, and there exists a rearrangement of the same terms that converges to it. You can even rearrange to make the series diverge. This is the Riemann rearrangement theorem, and it is one of the most disturbing results in all of analysis. Rearranging the terms of a series and thereby changing its sum violates everything that ordinary arithmetic teaches about addition. Adding the same numbers should give the same result regardless of the order. Whether you count your apples starting from the red ones or the green ones, you end up with the same total. Whether you add your expenses in chronological order or reverse chronological order, the total does not change. Except it does for infinite series. The key distinction is between absolutely convergent series and conditionally convergent ones. A series is absolutely convergent if the series of absolute values, replacing each term with its positive counterpart, also converges. The alternating harmonic series is not absolutely convergent. The harmonic series 1 plus 1/2 plus 1/3 plus 1/4, all positive, diverges. So the alternating version converges only conditionally, only because the signs are arranged to produce enough cancellation. Riemann proved that absolutely convergent series are safe. Their terms can be rearranged freely without changing the sum, but conditionally convergent series are vulnerable. Rearrange their terms and you can get any sum you want. The reason this works is related to what we discussed with the harmonic series. The positive terms of a conditionally convergent series sum to infinity on their own. The negative terms sum to negative infinity on their own. And you can add the two infinities in any ratio by choosing how many positive terms to take before taking each negative term, steering the partial sums to approach any target you name. What Riemann's theorem reveals is that addition for infinite sums is not the same operation as addition for finite sums. For finite sums, the commutative and associative laws hold unconditionally. For infinite sums, they hold only for absolutely convergent series. Conditional convergence is a weaker and stranger phenomenon, where the value of the sum depends not just on what you are adding, but on how you are adding it. This has consequences for physics and engineering, where infinite series appear constantly in approximation methods and perturbation theory. If the series being manipulated are only conditionally convergent, rearranging terms without care can produce incorrect results. Historically, some physicists and mathematicians used formal series manipulations without checking convergence conditions, and occasionally got the wrong answer as a result. Whether the rearrangement paradox strikes you as a problem with infinity, or as a feature of how addition works that finite arithmetic simply did not reveal, depends on your mathematical temperament. Both views are defensible. Infinity behaves differently from any finite quantity, and the rearrangement paradox is one of the clearest demonstrations of how different. You have the same ingredients, you mix them in different orders, you get different results. At what point does that stop being a property of the mixing and start being a property of the ingredients themselves? There is a way to understand why the rearrangement theorem works that makes it feel less like a paradox and more like a revelation about what conditionally convergent series actually are. When you add up the terms of the alternating harmonic series in the standard order, 1 minus 1/2 plus 1/3 minus 1/4. The cancellations happen in a specific pattern. Each positive term is followed closely by a negative term that partially cancels it. The partial sums stay close to the eventual limit and approach it steadily. The specific pattern of cancellation is what produces the specific value. When you rearrange the terms, you change the pattern of cancellations. By taking more positive terms before each negative term, you allow the partial sums to rise higher before they are pulled back down. By taking more negative terms before each positive term, you allow the partial sums to fall lower before they recover. And since the positive terms individually sum to infinity, and the negative terms individually sum to negative infinity, you have unlimited material in both directions. You can steer the partial sums to approach any target simply by adjusting how aggressively you take from each side before switching. The sum of a conditionally convergent series is really a sum of a specific pattern of cancellations. Change the pattern and you change the result, which suggests that the value of the series is not a property of the set of terms, but a property of the ordered sequence. The same set of terms, in different orders, has different sums. The order is as much a part of the mathematical object as the terms themselves. This is related to something that came up with the Ross-Littlewood Paradox. Order matters enormously for infinite processes. For finite processes, you can add numbers in any order and get the same total. For infinite processes, the order is part of the structure, and changing it changes the result. Finite intuitions about the commutativity of addition simply do not extend to the infinite case, at least not for conditionally convergent series. Whenever you summarize information by mentally adding its components, you implicitly choose an order. For finite collections, that order does not matter. For large collections where components pull in opposite directions, the order can affect the conclusion. Two people surveying the same evidence in different orders can reach different conclusions, not because of bias but because of the same structural feature Riemann identified. Some rearrangements destroy convergence entirely, producing partial sums that oscillate and never settle. Order can determine whether you reach any conclusion at all. Riemann proved every real number is achievable by some rearrangement of the alternating harmonic series, which means the value of the series is not a property of its terms alone but of how they are arranged. There is no fixed value without a fixed arrangement. Change the arrangement and you change the sum, or eliminate it entirely. How many things you treat as having fixed values are actually arrangements someone chose at some point? And would different choices have given different results? For infinite series, provably yes. For everything else, probably more often than you think. The rearrangement that reaches any given target value is determined by an iterative process. Take positive terms until you exceed the target, then take negative terms until you fall below, then positive again, oscillating and gradually converging. The process always works, but the resulting arrangement looks nothing like the original sequence and bears no obvious relationship to the value you were aiming for. The series reaches every value. None of them are visible in the terms themselves. They are all hiding in the order, waiting to be unlocked by whoever decides which arrangement to use. And most arrangements unlock nothing that converges at all. That is a strange kind of object to be dealing with.